दसाडे सर 10 वाजलेत. प्राचार्य जॉईन झालेत. हो. हा 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 तुम्हाला अनम्यूट करायला ऑप्शन आहे. हा झालेत. तुम्ही अनम्यूट होता येते का बघा तुम्हाला.
चालू करूया.
नमस्कार दसाटे सर.
नमस्ते गुरुदेव.
गुड मॉर्निंग सर.
नमस्कार. गुड मॉर्निंग डोबरे सर. गुड मॉर्निंग नवले सर.
हाँ नमस्ते सर. नमस्ते.
चालू करूया सर.
येस यस आय एम रेडी. प्लीज.
प्राचार्य साहेब आलेत ना.
हो आलेत सर.
ओके डोंगरे सर स्टार्ट करा.
ओके सर.
रेकॉर्ड चालू करा.
Recording in progress.
Okay. Good morning.
Okay.
Warm greetings everyone. I, Dr. J.V. Thomre, convener RTNA 2023. Welcome everyone to RTNA 2023. It gives me a great sense of joy to organize the event every year in our college and invite guests so that they can also become a part of our program and we can bond over in a healthy socio-cultural environment. We, the Department of Physics and IQAC, Vidnyan Mahavidyalaya Sangola, Taluka Sangola, District Solapur, Maharashtra, India, welcome you for 2 days international e-conference on recent trends in nanomaterials and its applications, RTNA 2023. Myself, Dr. J.V. Thomre, convener, Dr. S.S. Dasade, the IQAC coordinator, Dr. B.B. Navle, the head Department of Physics, Mr. A.M. Kamble and Dr. D.K. Bandgar, the member of organizing committee, Professor S.M. Mulani sir, the organizer and principal of our college, have taken efforts to make this e-conference successful along with entire teaching and non-teaching staff of college. Department of Physics is one of the leading department in the institute, having 4 permanent faculty members. All faculty members are doing research in various fields such as electrochemistry, gas sensors, solar cell, supercapacitors. The RTNA 2023 aims to provide terrific opportunities for academicians, researchers, scientists, engineers and industry representatives to network and share their knowledge, insightful suggestions and cutting-edge research in the field of nanomaterials. Furthermore, RTNA 2023 will provide a global podium platform discussing research concerns, challenges and solutions as we go into nanomaterials and its applications is undergoing transformations. Material scientists synthesize a new material for applications which has led to the development of everything from variety of applications including electronic components, electrochemical devices, sensors, microchips, ICs, etc. We feel that RTNA 2023 will provide an outstanding opportunity to expand our understanding and generate innovative ideas to aid in the advancement and evolution of cooperative academic research that is part of national education policy. We believe RTNA 2023 will be an outstanding venue for knowledge exchange and strengthening of new collaboration in the field of nanomaterials and nanotechnology. Research is getting more borderless as the field grows more borderless. The RTNA 2023 will focus on the most recent international advancement in nanomaterials with a particular emphasis on multidisciplinary research in both basic and applied domain. For better exposure of research on graduate and postgraduate student, Department of Physics in collaboration with IQAC has organized RTNA 2023. We are starting with inaugural session and keynote speaker is Professor Dr. P.B. Patil sir from Punyashlok Ahilyadevi Holkar, Solapur University, Solapur. And President is Professor S.M. Mulani sir, Principal of our college. I request IQAC Coordinator Dr. S.S. Dasade sir to share welcome address and to introduce today's keynote speaker, Professor P.B. Patil sir. Dr. S.S. Dasade sir, it's over to you.
Thank you. सांगोला तालुका शेतकरी शिक्षण प्रसारक मंडळ सांगोलाच विज्ञान महाविद्यालय सांगोला डिपार्टमेंट ऑफ फिजिक्स in collaboration with Internal Quality Assurance Cell organizes an international e-conference on recent trends in nanomaterials and its application 2023. The President of inaugural session, Honorable Principal of Vidnyan Mahavidyalaya Sangola, Dr. Sikandarji Mulani, Chief Guest of the conference and Guest of Honor, ex-Pro Vice Chancellor of Punyashlok Ahilyadevi Holkar, Solapur University, Solapur, Dr. V.B. Patil, foreign invitees and participants of the conference. My dear friends, ladies and gentlemen, I am immensely happy to welcome you to e-conference and to Vidnyan Mahavidyalaya to the International Conference on Recent Trends in Nanomaterials and Its Applications 2023. At the outset, let me record my gratitude to the directors of Sangola Taluka Shetkari Shikshan Prasarak Mandal Sangola and especially to the Honorable President and all directors for planning this conference. And thanks to my colleague in the college for entrusting the responsibility of organizing the conference to me and Dr. J.V. Chombre. Our aim in organizing the national or international conference or the event is to motivate and promote the student and research scholars, especially from villages. Dear friends, we have made every possible efforts to make this digital platform better and comfortable. Should there be any problem whatsoever, you can approach the organizers. I extend a warm welcome to one and all and wish you a very pleasant and fruitful with this digital platform with us. Now I would like to introduce Honorable ex-Pro Vice Chancellor and Chief Guest of the inaugural function of this international conference. It is my great pleasure to introduce Dr. V.B. Patil. He did MSc and PhD in Shivaji University, Kolhapur. He is working as a professor in his research lab, School of Physical Science, Punyashlok Ahilyadevi Holkar, Solapur University, Solapur since 1998. His areas of expertise in the field of material science, especially in the field of conducting polymer-based gas sensors and supercapacitors. He is also expert in hybrid solar cells. He has published 175 research articles in corpus indexed well-reputed impact factor journals and 184 research articles in Google Scholars. He has also published 104 articles in national and international conference. He is having H index of 52. His citations are above 7,000. His ITA index is 120 and he is having total impact factor of 624. He has published 8 books in Lambert Academic Publishing Germany, 2 books in Nirali Publication Pune, and he has 8 book chapters in Noah Publishers, New Elsewhere and Springer. He has completed 7 research projects and he is having 4 ongoing projects. Total research gas issued against this project is 1 crore 11 lakh 39,250 rupees. Dr. Vikas Patil has filed and finalized 4 patents in year 2017, 2020, 2021, 2022. He is member of various authorities, bodies and committees in various universities and well-reputed institute of government. Dr. Vikas Patil is acted as in-charge Vice Chancellor, Solapur University, Solapur. He did work as in-charge Pro Vice Chancellor, Punyashlok Ahilyadevi Holkar, Solapur University, Solapur. He is acted as an officer on special duty He is also acted as in charge Registrar Solapur University. He is chaired as a board of Dean Solapur University. He is also chaired as a director of School of Physical Science, head Department of Physics, head Department of Material Science. He is also chaired as a program officer NSS Solapur University Solapur, member of Academic Council Solapur University, member of Management Council Solapur University, Director Research and Development Cell Solapur University Solapur, member secretary of Intellectual Property Rights Cell Solapur University Solapur. He is honored with International Innovation and Research Excellence Award 2021. He was included in World Top 2% Scientists in Physics by Scientific AD Index and Stanford University in 2021 and 22. He is becoming honored by Best Teacher Award, Solapur University Solapur. He is also honored with Shikshan Ratna Award, Lok Mangal Foundation Solapur. He becomes as a Young Scientist Fellowship, Department of Science and Technology, New Delhi in March 2008. He got 11.13 lakh sanctioned under Fast Track Young Scientist Scheme. He also got Summer Research Fellowship, Physical Research Laboratory, Ahmedabad in June 2004. He is also honored with Summer Research Fellowship, Indian Academy of Sciences, to work at Indian Institute of Science, Bangalore during July 2006. Dear friends, we were here with this honored personality on this digital platform. Thank you, sir. Thank you so much. With this, I invite Dr. V.B. Patil to inaugurate this international event by keynote address. Over to Dr. Vikas G. Patil, my best friend and head Department of Physics, Solapur University, Solapur. Thank you,
Good
sir.
morning. Namaskar to all. Thank you for kind introduction, Dr. Dasade sir. At the outset, let me thank Principal of the college, Dr. S.M. Mulani sir, IQAC Director or the Coordinator, Dr. S.S. Dasade sir, Head of the Department of Dr. B.B. Navle sir, Convener of this conference, Dr. J.V. Thombre sir, Dr. D.K. Bandgar, Dr. Kamble, and whole organizing team of this international e-conference on recent trends in nanomaterials and its applications, organized by this Department of Physics, Vidnyan Mahavidyalaya, Sangola. It is indeed pleasure me to inaugurate this conference, e-conference, and I declare that this conference is inaugurated. Also, I have pleasure to share ongoing research activities. Presently, we are doing on gas sensors and supercapacitors at Functional Materials Laboratory at School of Physical Sciences, Punishlook at the Solapur University, Solapur. In that present scenario is that we are moving towards the means we are going in the phase of implementation of national education policy, and in this context, the topic selected for this conference is worth, and surely it will be beneficial for the research students and the faculty, those who are working in the field of material science, advanced material science, and its applications in the energy storage devices, energy harvesting devices. During my talk, I will explore about the various materials we have developed at FMRL for the energy storage applications as well as the gas sensors. So, you know that the present scenario is that there is due to the globalization of there is tremendous growth of the industries, automobiles, and due to that, no doubt this is beneficial to the society. But on other side, so during various process of the industrializations or automobiles, the various gases are involved in that, and these gases are hazardous to the human being. And like the gases like NOx, that is NO2 is there, NO3 is there, NO is there, SO2, SO3, carbon monoxide. So these gases, they are evolved during various industrial process or the automobile motor. Therefore, there is a need to detect these gases because the concentration of these gases are very small, and some of them are volatile or the non-volatile. So therefore, so there is a need to detect these gases, that concentration of these gases. Every these gases, that is maybe a NOx or maybe a SO3 or maybe carbon monoxide. So these are hazardous, and its concentration below 50 ppm parts per million. So it is okay, but above 50 ppm, so these are toxic ones. Therefore, there is a need to detect these gases, hazardous gases, okay, for the sake of the human being. And in our FMRL, we are working last 25 years, and we have developed the systems based upon various functional materials, okay, to select these gases. And so we have also designed the systems for detection of like ammonia, like ANO. And during my talk, I will explore and I will show you that is the systems we have developed. Another system, it is related to the energy storage applications. So you have that presently everywhere is the word EV is famous. Okay, that is EV vehicles, electric vehicles. Now the everyone, that is two-wheelers and four-wheelers. So okay, so they are now in the EV mode, or I mean the hybrid modes. Therefore, there is need to store uh, the particularly this energy. And presently, what is the scenario? So we are using a lithium and ion batteries. The present scenario is based upon the lithium and ion batteries. Okay, but the sources of lithium and ion, these are limited, and so it is not long term so beneficial. Okay. So that the people are searching, scientists are searching for the alternative for lithium ion batteries. And so presently, the scientists, the scientific community, they are going towards the supercapacitors. And so basically, lithium ion batteries are there. There are various advantages of these supercapacitors over the batteries. In due course, I will explore about this. So this means we are working on the gas sensors and the energy storage device like a supercapacitor materials. And so we have developed some supercapacitor devices based upon the conducting polymers and the metal oxide, because we are expertise in the development of the metal oxides and conducting polymer at our laboratory, that is the functional material research laboratory. And so we are not used, that is the sophisticated instrumentation for the development of the supercapacitor and the toxic gas detection system. Basically, today I'm dealing with the nanomaterials, and these nanomaterials are the functional nanomaterials. Basically, the function. What is actually the functional nanomaterials? Okay. Basically, then it is one material. It finds a diverse applications. For example, so zinc oxide is called as a functional material, or TiO2 is called as a functional material. For example, so TiO2 is a material. It is prepared by the chemical by deposition. It is prepared by hydrothermal. So different kinds of the physical and chemical approaches were used to devise or to fabricate the functional material as a TiO2, and it gives a various diverse kind of these structures, nanorods, nanowires, nanoparticles like that, and it finds a different application. Means one material having different forms, different structures, different morphology, and a different applications. So that TiO2 is called as the functional material. There is one material. If the one material having a diverse applications, so it is we can say that this is the particular is a functional material. So this TiO2 having a very good antimicrobial properties. And recently, so during the COVID pandemic, so our lab have developed a mask, and we have received the patent from the Indian Patent Office, Mumbai. So we have used this coating, inner coating of mask. So it is of a TF, and it is proved that it is a antimicrobial. Already it is used in the medicinal tablets as antimicrobial. So that means these are the functional materials. Example of one example is the functional. Same fashion, zinc oxide is there. It is widely used in the solar cell as a window material. Okay, so it is used as a electrode material in the supercapacitor. It is used as a best NO2 sensor. So that means zinc oxide is a functional material. Means it the one material having a diverse applications. So these functional materials, and at our laboratory, at functional materials laboratory, we have developed these kind of the functional materials by very simple approaches by using the chemical and uh, physical approaches for the energy conversion, for energy storage, gas sensors, and the energy storage as a supercapacitor. Okay, basically, there are various forms of the functional materials. Like these are zero dimensional, one dimensional, two dimensional, and the three dimensional. Okay, and there may be a dots, there may be a nanowires, maybe flowers, and they are engineered by chemical as well as the physical processes. Just I'm exploring the uh, my presentation, and to this presentation, basically it will provides you the insight of the various functional materials we have developed at our laboratory for the gas sensing applications and the energy storage applications. So, so I will during my talk I will cover about the introductory part of the nanoscience and nanotechnology, various approaches of the nano fabrications and its applications as sensors, energy storage, and the energy storage and some gas sensing applications. Okay. Before we go into see the different approaches of the engineering of the smart nanomaterials or functional materials for the gas sensing and energy storage applications. I would like to explore about why there is a delay in the nanotech. So just see now see some famous go wrong. So in 1901, scientist Wilbur Wright, he predicted that humans will not fly for another 50 years. Okay. In 1901, he has predicted. But what is the present situation? Everyone is flying. So different companies are there. Okay. So that means every person's he has having the flying. Okay. Now in 1943, the well-known scientist he stated that that is Thomas Watson. He stated that I envision a world market of about 5 computers at that time in 1943. So he has stated that only 5 computers will be sufficient. But now every person having his own systems, maybe laptops, maybe tablets. Now in the cell phones, so means we can use cell phone as a tablet or the this statement is also as per as the today's scene. In 1997, Neil Olson, he stated that no one need to have a personal computer at home. But what is the present situation? Everybody having desktops, laptops, and PCBs. So this statement is also wrong. And recently in 1981, the scientist Bill Gates, he said that 640 kilobyte of memory will be sufficient for storage of the data or for working on any mathematical analysis or statistical analysis or the word processing. But what is the scenario? So now we are using a hard disk like biscuit size of the hard disk, and the size is 5 TB, and this is not sufficient. Means we can say that. So that is prediction about the future is a difficult one, and it is given. The slogan is given by the scientist Neil Bohr, great physician, and he has explored the atomic model. Okay. He stated that we can't predict about the future, but the scientists at that time, and the scientist, the Richard Feynman, who explored the word and the meaning of the nano. That is, he said that there is plenty of rooms at the bottom. Means, and he has explored the meaning of the nano. That is, N for the novel, A for the approaches, N for the new, and O for the opposites. Novel approaches and new opposites. Novel approaches and new opposites. For example, which I have mentioned during the introduction, that is, TiO2 and zinc oxide, these are the functional materials. Means you can use an approach. Approach means different kinds of the methods used for the preparation. Okay, TiO2 in general, which TiO2 is prepared by chemical by deposition, hydrothermal, or other thermal evaporation also. Zinc oxide is also same by different physical and chemical approach. Means the no, you can use a novel approach, you will get a new approach. Means you can use it for the microbial application, antimicrobial application. You can use for gas sensor. You can use for the energy storage applications. You can use for the electrochromic applications. Means diverse applications. Means if you can use the novel approaches, so you will find the diverse applications of these functional materials. Okay, just see. Always you observe the nature. Just see. So this is the common thing, but at that time, so it is uncommon. Why? Because in ancient days, the technology is not developed. So in our time also, so we are making this, that is with the help of the wire, okay, or stick, we can make a wrinkles on the water. And just see, it is like a coral structure. It is like a coral structure. It is like coral structure. In the inside, this one structure is given. It is iron structure. Iron structure is a coral-like structure. If you compare this, so it is same as. But in earlier days, the technology is not developed. That is, scanning tunneling microscope is there, or we can say that transmission electron microscope is not there. Field emission scanning electron microscopes are not there, as well as the atomic force microscopes are not there. Means we can view the two-dimensional or three-dimensional structure with the help of the atomic force microscope. Okay, means at that time, in ancient ancient days, the technologies are not developed, so that not possible to get the information about the nanostructure. Another example. Okay, look at the nature carefully. This is the lotus flower, and on the lotus flower there is a water droplet. Water droplet. Okay, and in the insect shows the scanning electron microscope of the nanomaterials. Okay, means maybe the micro or these are the nanostructures of the waxy surface. So we can say the super hydrophobic structures. So basically, super hydrophobic means when you have that one system is there called as the contact angle measurement, and with the help of this instrument, you can confirm that your surface is a waxy. That is super hydrophobic or super hydrophilic. Super hydrophobic, it is a means if the contact angle, that is, you can say the theta, if it is greater than 150 degree, so it is called as your material is a super hydrophobic. Okay. And if it is super hydrophobic, below theta is less than 5 degree, you can say that super hydrophilic nature. Means about the waxy surface, you can get the information if the contact angle meter is available. Means nowadays the technology is there, so that you can say that, so that this is the hydrophobic structure, this is the hydrophilic structure. Okay. Now just see the water strider, and in the inside these are the field emission scanning electron microscope of one functional materials. So one is at 20 micrometer, another is at 200 nanometer. Just see, so water strider kind of the morphology, one material, maybe zinc oxide, maybe metal oxides, maybe the metal, or maybe the polymers. Okay, so it gets the structure like a water strider. So we can say that it's the water strider kind of the morphology. No, it plays a vital role in the various applications. Means one morphology is not useful for the gas sensor. The another is for maybe this such kind of the morphology used for the supercapacitor application. For example, for gas sensing applications, the porous morphology is very useful. Okay, because gas should be adsorbed there and easily dissolved there. So adsorption, such kind of morphology is important. But such kind of the morphology is not used for usable for the supercapacitor applications, because for it requires compact kind of the morphology, because there is a conduction of the electron is contiguous in case of the energy storage device like a superconductor. So supercapacitor. So means the one, but also the zinc oxide may be a spongy, or you can say that porous morphology, or maybe compact. It depends upon the novel application. Okay, so this is the nano kind of the structures. One is the mosquito structure, and this is the inside show the morphology of the structure. Okay, yes. Now the feet of the lizard, and this in the inside. So we see here there is a feet of lizard kind of the field emission scanning electromagnet. Such interesting morphologies may be viewed by using the advent of the nanotechnology or nano instruments, that is the field emission microscopes or transmission electron microscopes. Then what is the nanotechnology? That is the creation of the functional materials, devices and systems. That is, you can create the functional materials, device and the systems through, we can control the size of the nanomaterial, that is 1 to 100. Generally, we can say that nanomaterial means its size, it is from 1 to 100 nanometer. We can say that it is the nano. Okay. Above 100, we cannot say it's the nano. People are saying nano, that is 500 nano they are saying. In the field emission scanning microscope, they are getting the information about the clusters, and they are saying 500 nano. It's wrong. Okay. From field emission scanning microscope, you will not get information about the size of the particular structure. You will get the morphology. Okay. Now, there is the creation of the functional materials, device and system. So this is by exploiting the novel properties and the phenomena at a very all length scales. So this is simply the nanotechnology, creation of the nanomaterials, creation of the functional materials. So in the particular range of 1 to 100 nanometer, and if it is the case, then we'll get a diverse applications of these materials. Then why nanomaterials? Size-dependent physical chemical properties. Size-dependent physical chemical properties. So size of the any functional materials or the nanomaterial plays a vital role in the applications. Okay, because for example, we can say that cadmium sulfide is well-known material used for the solar cell applications, because its band gap, it is a 2.46 electron volt. So usually it is used for the solar cell applications. But if it is size is same, then it is used in the drug delivery system. And nowadays, the cadmium sulfide used in the drug delivery system. PiO, its size is also very small, and it is used in the antimicrobial applications. Means the size-dependent physical chemical properties are there, that they are useful for the diverse applications. Okay, so these are so it is a use of these nanomaterials. Now, there are various kinds of the nanomaterials as zero-dimensional. Zero-dimensional nanomaterials called as the quantum structures. One-dimensional called as the nanowires. Two-dimensional, these are thick and thin films. Three-dimensional is the bulk nanostructure. Generally, so there are three parameters. It is length, breadth, and the heights. And according to these three parameters, you can classify them as zero-dimensional, one-dimensional, two-dimensional, and a three-dimensional. So in zero-dimensional, generally, the three parameters, they are centered at a one point, single point. This is called as the zero-dimensional. And best example of the quantum dot zero-dimensional, it is called, these are the clusters or the spheres. So in that case, the length, breadth, and their height, they are confined or concentrated at a single point. It is the zero-dimensional. One-dimensional, it has only one parameter, maybe length, or maybe the breadth, or maybe the height. So nanowires, nanorods. So these are the well-known examples. If there is a horizontal growth, you can say that nanowires, horizontal growth. And vertical growth, that is vertical growth, it is the nanorods. Okay, so the one dimension. Two dimension, it has length and the breadth. There is nanofilms, plates, nanoplate structure. There are carbon materials, so therefore in the two-dimensional structures. For example, some metals. For example, the metal, the MOS2, WS2, MOSC2, like that. So this metal sulfides, Okay, so cobalt sulfides, these are the two-dimensional metals. So two-dimensional metals are very good because they are sheet-like material. Now we are using in earlier days, graphene metals or carbon metals, they are used as its morphology is a sheet-like morphology, porous morphology. Okay. But nowadays, alternative for carbon is a two-dimensional material because it have a plate-like structure, and the structure of the two-dimensional material it is similar to that of the graphene structures or carbon structures. Okay, because now world is saying there is carbon-free. Everything is carbon free, so that the researchers they are finding novel materials by again it is by using the novel approaches. The well-known example just I have explored is the MOS2 and the MOSC2 is there. The three-dimensional bulk nanostructures. Nanoparticles are well-known example. Nanoparticles are the well-known example of the bulk materials, and it has three parameters there. They are having a length, they are having the breadth, they are having the reason. And there are various forms of the nanomaterials are there. Nanoparticles, nanotubes, nanosprings, nanobelts, quantum dots, okay, nanowires, nanofibers, nano fluids also. Okay, so according to structure, the people are saying these are the structures. Now, there are various forms of the nanometals. There may be a single particle that is in the powder form. There may be a thin film form, multi-layer form. They are the colloids in the liquid form. Okay, and all these may be metals, semiconductors, and the instruments. So these are the various forms of the nanomaterial. Now, basically nowadays two technologies were used to grow the various nanomaterials or functional materials. Okay, two approaches basically used. One is the top-down approach, and another is the bottom-up. This top-down approach, it is a complicated one. Okay, and as mentioned, or it is explored in the slide because this top-down approach means the fabrication of a device structure through the monolithic processes of the nanoscale, and it requires the sophisticated instrumentations. Okay, for example, you know that the single crystal of silicon, so various transistors and MOSFETs, okay, the devices, that is IC fabrication, it is carried out with the help of the top-down approaches. Lithography technique is there, and it requires special pen that is and atomic force microscope that is required structure you have to draw with the help of this pen, and it is costlier one. So it is a tedious one. It is not a simple way to get the nanostructure. But the bottom-up approaches are simple. I will show you the bottom-up approaches we have used to grow the various nanomaterials or various functional materials for the various applications. It's very simple. So assembly of the atoms, molecules, or other basic means you can rearrange. You can rearrange the atoms or the molecules. Okay. So, for example, we are doping some metals or the non-metals into the host materials. So, what is the purpose of that? You can change the properties of the metals. After doping, you will get the enhanced properties of gas sensing or supercapacitor or solar cell. Okay, so that such kind of the facility is available in the simple materials, simple approaches of the nanotechnology. And just see these are the various approaches of the nanotechnologies. That is the physical approach. Physical approach, for example, just see physical process of physical approach, top-down approach and bottom-up approach. Just see the example of top-down approach, that is the lithography and ball milling. Let's see the top-down approach is the lithography. So for lithography, okay, it requires a monolithic surface like a single crystal of silicon. For example, so you know that IC fabrication technology. There is one is a small scale integration, large scale integration, medium scale integration, and very large scale integration. Now these four technologies are unavailable. Now we have to grow the transistor according to the Moore's law. Okay, means how many components are there? grow on the single crystal of silicon. Means single crystal of silicon, it is a, in earlier days, you know that the Jagroski's method is used to grow the single crystal of silicon. Okay, seed method, called a seed method. Okay, by using the seed method, you can grow single crystal of silicon. And so it has a single phase, or we can single crystal of silicon. And you have to make a slice, and you have to make a cut of the anywhere to the single crystal of silicon. So you'll find the all dimensions are okay. And you have to write. You have to write means you have to draw the components. You have to mount the components, okay, according to your requirements. If you can grow the 5 components on the crystal of silicon, okay, so it is a small scale integration. That is, you know that that is from, for example, there is IC packaging technology there. That is, if you can mount 1 to 9 components on a single crystal of silicon, you can say that it is small scale integration. If you can grow, that is 10 to 99 components on single crystal of silicon, it is called as the medium scale integration. If you can grow the 100 to 1099 99 components on single crystal of silicon, you can say that the large scale integration. And above 1000, if you can grow the components, that is up to 10,000, that is 1000 to 10,000 components mounted on single crystal of silicon, slice of the silicon. Okay, so Moore's law increases. The number of compounds are increases. It's called a Moore's law. Okay, and so there is more than 10,000 compounds that are mounted on a single chip of silicon. Okay, and this technology is done by the lithography. Just, but it is not possible. It requires a sophisticated equipment. A pen lithography is required. Single crystal of silicon is required. To grow single crystal of silicon, it requires the Jagroski's method, chunk required, okay, because it requires a temperature is above 1400 degrees Celsius, okay. So seed is required. So means lot of infrastructure required to grow the nanomaterials by using the physical approach, top-down physical approach, okay. But as compared to the top-down approach, bottom-up approach of a physical process is okay. I'm saying okay, no, but not saying the very good. Physical vapor deposition, chemical vapor deposition, pulse laser deposition, molecular beam protection, sputting. Okay. So these are the systems required for that. But for physical vapor deposition, simply called a thermal evaporation. What is a thermal evaporation method? Okay, so it requires some costly, but you will get the very good quality of the nanostructure by using the bottom-up approach of the physical. No doubt. Top-down approach also you will get a good quality or excellent quality nanofabrication. But these are costlier. It requires the sophisticated instrument like atomic force microscope. Its cost is above 1 crore. It requires a single crystal of silicon grow chunk or seed crystal for that. Its cost is above 1. So this requires sophisticated instrument. But so as compared to the cost, so bottom-up approach of physical processes are good to grow the nano crystals. On the other hand, the chemical process, just see the chemical process. So the top-down approach, chemical etching. No doubt, chemical etching is also costlier one. But nowadays, the researchers, so like us, we are using the bottom-up approach of a chemical processes to grow the various kinds of the nanomaterials for the diverse applications, like the soil gel, like a hydrothermal, like a chemical bath, iller deposition, and spray pumps. Its cost is spinning girls. Its cost is below 5 lakhs. Some systems require only 10,000 rupees. At your laboratory, you can grow the desired nanostructures at your laboratory. Cost is 10,000, only 10,000. Just I'm showing you, I'm exploring. Means the instrument is not, or the facility is not the important thing. Is that what kind of the nanostructure you can grow by using the simple tech. Okay, just see. And this choice is in your hand. Just see the slide. In that case, you can, by using simple way, you can grow the nanostructure. What is the one flask? Thermometer is there. Okay. And only thing is that only two, three things are there. Okay, at your laboratory you can grow the single crystal, not a single crystal, but you can grow the nanostructures. Okay, and same nanostructure may be grown by using the complicated one. So just see, this is a molecular beam epitaxy. The complicated schematic is showing in the slide. So it is a molecular beam epitaxy. So it requires vacuum, it requires various globe boxes, okay, but quality of the nanostructure grown by using the maybe is good as compared to the simple method. Means actually basically the choice depends upon your money and the expertise available. For simple methods, so expertise is not needed, but for complicated one, you should be expertise to handle such kind of the system, because molecular beam system, its cost is above 3 CR. So it requires a clean room. Okay. So the whole setup will be hosted in a clean room, and the size is also very. So means choice depends upon your money and the expertise available. Now I'm just displaying the methods we are using, because time is a constant. I want to show the applications part also. Just see, so these are the methods actually we have used to grow the nanomaterials. Just see, the sol gel method, and by using the sol gel methods, basically in sol gel methods, I'm showing you we have grown different metal oxides like the N-type metal oxides and P-type metal oxides by using the sol gel method. Is a very simple method, chemical method. It requires only a glass beaker and magnetic stirrer. So you have to add the temperature up to 80 degrees Celsius. And for that purpose, it requires a source material as a metal alkoxides and a solvent like the organic solvents like ethanol as well as the methanol. Only two things are required. One thing is required, the metal alkoxides and the solvents like ethanol and the methanol. And you take an appropriate amount of the particular metal oxides. For example, so we have prepared SNO2 and alpha epitope nanoparticles by sol-gel process. So we have used here for the fabrication of the SNO2 nanoparticles, we have used the stannic chloride hexahydrate. SnCl6, SnCl2, 6H2. So this is a stannic chloride hexahydrate, 6H2. And so this is the metal oxides we have used in the powder form. And we have used the methanol as a solvent. Appropriately, we have added into that. And we have stirred at a particular 60 °C temperature on the magnetic stirrer. And the RPM rate is nearly 100 to 150, okay, 150 RPM. Okay. And so we have stirred this for the 1 hour, and after 1 hour, the first thing, it is the sol formation. That is, once you can add a metal alkoxide plus organic solvent like methanol, ethanol. So there is a formation of a sol formation at a temperature of a 60 degrees. Okay, and after half an hour, you will get the sol gets, the water is evaporated and the organic solvent is not water. Organic solvent is evaporated from the mixture, and the condensation takes place, and you will get a very fine powder of a metal hydroxides. It is metal hydroxide. It is a SNO2, therefore is a tin hydroxide, and after annealing about 200 degrees Celsius, after annealing about 200 degrees Celsius, you will get very good kind of the SNO2, pure SNO2 nanoparticles. Similar kind of the alpha we have grown, W3, and just see, I'm showing you the various kind of the structures. These are just see the morphologies of the zinc oxide nanoparticles, alpha nanoparticles, W3 nanoparticles, TR2 nanoparticles, SO2 nanoparticles, and nickel. So these different these are some cases. So I have explored here, and these nanostructures, these are the nanoparticles grown by using very simple sol gel method at our laboratory for the gas sensing applications. Okay. Now the chemical body portion is there. Just see the nanorod kind of the structure we have grown at our laboratory. Then another method is the hydrothermal method. So this advantage of the hydrothermal and the chemical body portion method So you can grow the metal oxides below 100 degrees Celsius. These are the advantages of the metal oxides. And one-dimensional morphologies. So one can grow with the help of the chemical bar deposition and the hydrothermal method. Okay, just see, these are the morphologies basically. These are the morphologies grown by using the hydrothermal method. So this is the morphology of the zinc oxide nanorods. That is one-dimensional zinc oxide nanorod, and they are vertically aligned nanorods. And the nanorods of the WO3 and the TiO2 nanorods grown by using the hydrothermal method, chemical method at our functional materials laboratory. Okay, and the growth is below 150 degrees Celsius. Means metal oxide, you can grow the metal oxides below this. Then the yellow deposit system is a very simple technique, and basically you can grow the coating of thin layer on conducting substrates. Here requirement is conducting substrates. Okay, and basically it is the basic principle of the yellow deposition. It is governed by the Faraday's law, that is oxidation and reduction takes place, and you can vary the current density or the voltage, and that we will say that it's a galvan static and the potential static. So by using these two way, you can grow the thin layer of metal oxides or metals or the simple polymers also, conducting polymers also for the supercapacitor application, because so it requires a conducting substrates, and conducting substrates are not favorable for, or not usable for, or not beneficial for the gas sensing applications. And the materials developed by the yellow deposition process used for the supercapacitor application. So these are the various morphologies. We have grown the polyaniline nanofibrous morphology, porous morphology, nickel oxide plate-like morphology, and the MNA2, the plate-like morphology. We have grown by using the yellow deposition. Okay. Now the spray pyrolysis, nano-noodles we can grow by the spray pyrolysis. Here also you can above 200 degrees Celsius you can grow the wide area nanomaterial by using the spray pyrolysis. Okay. Now I'm showing you the electrospinning process, and so flexible electrodes basically you can grow nano rod, nano wire kind of the morphology you can grow by the electro spinning process, and it is applicable for basically it is applicable for supercapacitor applications. You can see the various processes, very fine nano wires. The porous nanowires are grown by using the electrospinning material on the flexible electrode. These are the stainless steel electrodes. Okay, so this is the electrospinning, and just see the flexible. Okay, electrodes used for the supercapacitor applications. So there are some advantages of the chemical processes. Very simple, inexpensive. You can control the concentration, low temperature, large quantities. You can grow the liquid and things by using means variety of the materials you can grow by using the chemical. Now physical processes, thermal evaporation method. So this technique, the physical process is available at our laboratory. Okay, so you have to adjust here the vacuum and very good quality of the nanomaterial, one dimensional, that is nanowires, one can grow with the help of the thermal evaporation. You see, so these are the nanowires, bunch of the nanowires grown at our functional materials laboratory by using thermal evaporation method. Okay, so nano cubes and nanoflowers also grown by using the thermal evaporation method. Okay, heterostructures, that is nanowire and the nano particles. Okay, so heterostructures of the Chernova CU also grown. We have grown by using thermal evaporation. These are the field emission scanning microscope. These are the transmission microscopes of the various heterostructures. Just see here, this is the zinc oxide nano wire, and on which the copper oxide nanoparticles are added. So now the technology is available there, so that you can say that these nanoparticles there attached to the nano wire. Okay. Now chemical particle system also we have, and we have grown various nano wire zinc oxide nanowires, and heterostructure composed of the WO3 and copper oxide nanowires by using the chemical vapor deposition. So you can adjust the pressure, gas pressure, and by applying the proper gases like oxygen and the oxygen-like gases. Okay, what happened? We can control the morphology of the nanomaterial by adjusting the gas pressure or gas concentration, and you will get such kind of very good morphology of the nanomaterial. Okay. Now, so these are the materials we have grown by the very simple techniques, and we have used for the gas sensing applications. Okay, so just I mentioned in the introduction why there is a need of the gas sensor, because various gases are evolved during the various process of industries, automobiles, and spoiling the healthy life of the human being. Therefore, there is a need to detect these gases. Its concentration is very important. Some of the gases are volatile and the non-volatile. Therefore, there is a requirement of detect. So these are the various hazardous gases, their sources, and the major health effects on the human being. Basically, the ideal gas sensors, they should be very highly sensitive, should be having a fast response and recovery time. They should be a reproducible. They should be a stable. Okay, as well as they should be highly sensitive. Particular gas should respond to the particular gas only, and the good gas sensor should be having a low cost. So these are the ideal requirements of the gas sensors. Okay, so two technologies you can use the thick and the thin film technologies. So thin film means they're below 1 micrometer. We can say that thin film, thin films, and above 1 micrometer is there. Thickness is there. We say that the thick films. Both the films were useful for the gas sensor applications. Basically, so we have developed a chemoresistive gas sensors. Basically, chemoresistive gas sensors, the concept of a chemoresistive gas sensor, in that case, the substrate should be a non-conducting, and on the non-conductive gas substrate, the glass substrates, or you can say that the alumina substrates, okay, non-conducting substrate, on which you have to grow the sensor films, maybe the oxide, maybe the polymers, or maybe the kind of its composite or the heterostructure. That is the polymer and the metal oxide composite, or polymer or metal oxide heterostructure, or metal oxide heterostructures. Okay, and the electrons are drawn from this sensing film. So for the practical purpose, you can use the silver electrodes, and the resistance is measured by the high precision current meters or resistance meters. We have used here programmable electrometer to measure the resistance versus the time, and after measurement of the resistance versus time with a particular gas concentration and particular temperature. Okay, so you can measure resistance and time by the data access system connected to the computer. So means you can record this resistance versus time. So you will get a response time and the recovery time. Generally, the response time means the sensor material. So it changes. The changes from 10% to the 90%. The response or the resistance changes from 10 to the 90%. It is called as the response. How rapidly detect the gas from 10% to the 9%. And after that, it saturates. And after that, once the response is reached, the 90%, it recovers. And then 90% to the 10%, 0%, or 10% back to its original state. It is called as the recovery time. And from that means you can see the gas on and gas off. And you can find out the various parameters like sensitivity is very important. That is called a gas response. Yes, sir. Gas response basically it is a different. That is yes, R is equal to Rg by R air. If Rg means change of resistance in a gas media, and Ra means change of resistance in an air. S equal to Rg by Ra, or R gas divided by R air. This equation is valid for the oxidizing gases, and the R air by R gas, S equal to R air by R gas, So this is applicable for the reducing gas. Okay, but the one equation not applicable for reducing oxygen. For reducing and oxygen gases, the equations are different. Okay, so these are some sensors we have developed at our laboratory. Okay, different kinds of the gas materials are there. Inorganic material, organic materials, and the hybrid materials can use this. Okay, so basically, your gas sensor should be operated at a low temperature, should be a selective, should be a sensitive, and some metal oxides and gas bonding polymers. There are some disadvantages, and all these disadvantages are covered by the combinations of metal oxides and the bonding polymers. Okay, because it operates at room temperature, it is a selective, it is a reproducible, it is stable. Okay, such kind of sensors are useful for the device fabrications. Okay, these are gas sensing mechanism when the oxidizing and when reducing gas are interact with the P-type and the N-type material. So these are the gas sensing setup we have used. Okay, for the measurement of the resistance versus time. Okay, and now these are sensors we have developed. This is iron oxide sensor we have developed, and this sensor. Let's see that this sensor, it is a responsible for the NO2 gas, that is it detects the NO2 gas. Just see the linearity is very good. Okay, means it shows the response to the 10 to 100 ppm of NO2 gas at 200 degrees Celsius. Because metal oxide sensors, these sensors are not operated at room temperature because it requires, because these are insulating one. These are the Nano kind of the sensors. Okay, polymer sensors, just the polymer sensor. We have developed polyaniline based sensors. These are fibrous one sensors, and just see, so they are responsible for the ammonia gas, which it is the ammonia, and it advantage of the polymer sensor, basically it operates at a low temperatures, that is room temperature. The gassing mechanism, for example, the polymer chain, it is a N and EH there, NEHC is there, okay, and the ammonia gas, it is a reducing gas. When it interacts with the P-type of materials, it can, the reducing gas, it donate electron to the particular material, and due to that H plus ion gets out. The reduction means after electron take place here, so that there is a reduction of the H plus ion, and due to that the conductivity of the material decreases, because conductivity of the P-type material due to the holes, therefore conductivity decreases due to the H plus ion. There is a reduction of H plus ion, and therefore the resistance of the material or the polyaniline material is increased with the gas, when gas is infected. Very good response time and the recovery time is very good. So these are the sensors we have developed on flexible substrate. Okay, so just see various flexible materials we have developed, and it is seen that that is the composite material, that is Pani alpha to the material, shows the highest response to the ammonia gas. Okay, and pure single material is only 19.47% response for that. Okay, means hybrid materials are very good as compared to this polyaniline W3 material. Okay, the polyaniline W3 material, same fashion here. So by using the chemical process, that is chemical in situ method, so we have developed here polyaniline and W3 cell. Okay. In this case, we have added W3 nanoparticles into the polyaniline during the de-doping process, that is inserting form of the semi-conducting form of the polyaniline inclusion, and just see very fine the polyaniline W3 flexible sensor is devised, and just see the response of the polyaniline W3 sensor. It is a 120% response. Basically, it is higher at a polyaniline because it works at a room temperature. It works at a room temperature. At room temperature, very good response. Pani W3 have very good kind of the linearity, very good kind of the reproducibility, very good kind of the response and the recovery time, good kind of the stability is achieved for the polyaniline and W3 hybrid nanocompounds. Now, ammonia-based sensor, just the various sensors. Time is a constant, so that I'm showing you the various devices we have developed. So we have developed the sensors like I'm showing you here. Just a minute. The ammonia sensor we have developed at our laboratory, and we use the flexible polyethylene kind of the sensors. Next, just see this is the another sensors. Now, this is the another sensor we have developed. You see, very small amount of gas is impulsed. This is the AC based SC. So, very small amount of gas we have added in, and we have observed a very good kind of the ammonia sensor. So, this is sensor assembly. We tested our sensors on the ice industry, and where the ammonia gas is concentration very high. This is our sensor, and just see here. So these are the yes. It indicates there is a very heavy concentration of the ammonia gas. When the power is on, the gas is detected. Okay. Now, just see. This is the another sensor we have developed. Just see. You see, very small amount of gas we have inferred, and so the gas is detected. So the system will indicate that the gas detection, okay, through getting the buzzer, as well as we'll get information through the ACM, that is the message. It means if the gas leak is there in industry or in the home, so that you get information if you are outside also. So this system is we have developed laboratory. So these are the two patents we have grabbed from the Indian government of India patent office. Okay, it is based upon the ammonia gas sensor and the NO2 gas sensors. Now, so these are the various batches so of the gas sensor. That is the ammonia sensors and NOx sensors we have developed at our laboratory in a collaboration with one industry, and we have transferred this technology to the industry for the further development of the gas sensor, that is NO2 and the ammonia gas sensors. Okay, so energy storage device we are working on the energy storage application like a supercapacitor. We have devised various supercapacitor electrodes based upon the polyaniline as well as the metal oxides and conducting polymers. Basically, nowadays, basically supercapacitor devices, they are used to store the extremely large amount of the electric charges, and it stores, basically supercapacitor stores and release the energy by the reversible adsorption and reversible process. Just see the slide, and which gives you the comparison between the supercapacitors, capacitors, batteries, and the fuel cells. Basically, the supercapacitor bridges the gap between the batteries and the conventional supercapacitors. The supercapacitors, it provides very high capacitance. It offers longer surface, longer service, and long cycle. It has a higher energy density than the ordinary capacitors, as well as it has a very high power density than the batteries. Now we are using the lithium-ion batteries in the EV vehicles. Okay, but if you can use in a future a supercapacitor in the EV, so the advantage is that it has a high power density than the batteries. Also, therefore, they provides a large power burst for the short duration. And surely, in the near future, your EV vehicles, they will be based upon the supercapacitor. The processing cost of the supercapacitor is also low as compared to the lithium-ion battery. So that it is a very best alternative in the future for the supercapacitor. Various metals were used to fabricate the supercapacitor, conductive polymers, metal oxides, and pani and MnA2. So these are the that is a polymer-based supercapacitors electrodes we have devised. Very good kind of the supercapacitor, that is 508, 510 specific capacitance is achieved by for the polymer-based supercapacitors. Metal oxide-based supercapacitor we have devised. Then the hybrid supercapacitor we have devised. This is the hybrid, that is polyaniline and nickel oxide hybrid, and all their work at room temperature. Okay, very good oxidation reduction process is there. Okay, morpholysis is very good there. Okay, and so recently we have developed polyaniline and MnA2 hybrid supercapacitor electrode. Very good redox reaction takes place in the hybrid supercapacitor electrode devised by using the polyaniline and MnA2. Okay, and just see the efficiency is very good, specific power is very good, specific energy is very good, and SC is also very good. Okay, so there are various performance parameters of the polyaniline and MnA2 flexible electrode over the individual pani electrode and MnA2 electrodes. And just see these various processes they are involved in the fabrication of the symmetric supercapacitor. Okay, we have used the both electrodes are of the polyaniline and MnA2, so called as the symmetric supercapacitor devices. And here we have developed two cells on the flexible substrates. Okay, and they are connected in series. Only two cells. Just see. So we have tested in our laboratory these two cells. Okay, so just see it is charged for only a 10 seconds. Okay, we have applied some voltage to this 10 seconds. Okay, and so it will remain for the 40 seconds. 2 volt we have applied, and time is for the 10 seconds. So this is the charging. Yes. Now just see the discharging time. So discharging gas. Okay. Just see the ephemeral. Our lab logo is clone. So more than 50 LEDs glown by the two cells they are connected in series. Okay. So it remains for the half minute, you can say that. Earlier we have charged for the 10 seconds. Only two cells we have connected. So just see, this is device we have, and recently we have devoted our efforts towards the fabrication of the antimicrobial materials like TiO2, because we are expertise in, so that during the COVID pandemics, so we have developed antimicrobial materials at TiO2. We have received the patent for that, and so we have made the mask. The layer of the TiO2 we have used for the mask, and during COVID pandemics, it finds beneficial to protect from these COVID viruses. So these are the various facilities available at School of Physical Sciences. We have a BET surface analyzer, so you can get the pore size of the nanomaterials. Stylus propellometer, you can get information about thickness. So this is a UV visible spectrophotometer with us, that you can get information about the optical transmitters or the reflectors as well as the absorbers. Those who are working in the field of the solar cells. So this equipment is very useful. And BET surface analyzer, you will get information of the pore. Those who are working in the supercapacitor, those working in the gas sensor or the solar cells, the pore size is very important. Okay, so that the BT analyzer is here, and these equipments are purchased through the RUSA grant, and they are housed in the School of Physical Sciences. Those who wish to do the characterization of their materials, okay, so come to the department, come to the school, okay, and you fill the form, submit to the office. So you'll get this at a low cost, on the low cost of charges, and these charges are low for our college teachers and college students. So these are the prototypes that IPR developed by our functional materials and laboratory. We have developed omni sensors, two sensors. Then COVID pandemic also we have developed 4-in-1 machine and different kinds of the mass. So these are the various research facilities, and all these are indigenous. As per our requirement, we have developed these facilities, and from last 20 years we are using these facilities, and performance is excellent. We have developed gas as this one, room temperature gas that you need, and high temperature gas institute, and I proudly say that over 50 gas sensor units. Basically, this is our design, our ephemeral design, and we have transferred this technology to the Century Cooling System Solapur, and through which, so they have transferred these units to the people who are working in the gas sensor. More than 50 units of the gas sensor units. So they have supplied to the institutions and the universities where the peoples are working on the gases. I proudly say that. So few also the thermoelectric power in it, electrical conductivity, is an indigenous one, and also gives the best performance in the to get the information about the type of the conductivity, N type or P type, and the electrical conductivity, that is the resistance versus the temperature measurement, and hydrothermal unit. Its cost is only 20 to 30,000, but if you go into the market, so its cost is above 1 lakh. So as the cost effective, our systems are very good. So these are the facilities available at the functional materials laboratories, and all these facilities are procured from the research funds I received from the various funding agencies. So these are the prototypes, these are facilities again available at our functional materials laboratory, School of Physical Sciences. And finally, I'm very much thankful to my collaborator, Dr. DK Aswal sir. Presently, he's a director of National Physical Laboratory, New Delhi. Dr. S.K. Gupta, Dr. Shashwat, Dr. Nisragil. They are collaborated, and they are actively engaged with the research with my research group. And finally, I have received the funding from that is, I have received nearly 1.5 CR research fund from the RUSA, UGC, CSR, DST, and BRNS. And due to that, it is possible me to work in the diverse area like gas sensors and super capacitors. And finally, so the work presented by me, and this work is done by my all students, and I am happy to um, uh, let you know that all my students, they are placed in the very good institution. One of my student, Dr. S.D. Navle, presently, and he is the student of your Vidnyan Mahavidyalaya Sangola. He is presently working as a Marie Curie fellow. This is a prestigious European fellowship, and this fellowship received by the ephemeral student, Dr. S.D. Navle, and I proudly say that he's a student of my lab, as well as he's a student of the hosting college. This is proud to us. All other students are there working in the good colleges, good institutions, okay? And presently, few students are there working for their research in the advanced field of the functional materials. So that I have presented this work due to their efforts. Thank you very much. And at the end, I'm very much thankful to Dr. J.V. Thomre sir, Dr. Bhagwan Navle sir, Dr. My friend, all these are my friend, Dr. Dasade sir, and all the organizing committee team, and finally the chairman of this conference is Dr. Professor Mulani sir. He's a present principal and he's our best friend. Thank you very much. All here the those who are participated in this and they have my presentation. Thank you very much. Now I request all the participants to ask the queries. Thank you very much. Thank you.
Thank you, sir, for your nice presentation.
Thank you, sir.
Thank you very much, sir. Professor Patil, sir, has presented his presentation in a wonderful way. Professor Patil, sir, has explained some importance of RTNA 2023. Also, sir has explained the current trends in various applications like gas sensors, supercapacitor devices, solar cells, etc. Professor Patil sir has explained the special features of functional materials like zinc oxide, titanium dioxide and its uses in nanotechnology. Especially, sir has explained the basics of two approaches of the synthesis of materials like top-down approach and bottom-up approach with examples and synthesis methods. So thank you, sir, for sharing your views with us. Thank you very much, sir.
Thank you very much.
Dr. Thomre.
Yes, sir.
Take one or two questions or queries, please.
Participants are requested to ask. If you have any questions, then you can ask.
Hello, sir.
Yes,
this is Dr. from Dongu University, Seoul.
Yeah.
I want to ask a question to Patil, sir. So thank you so much for your wonderful and informative session. Especially, I was looking forward to it, and yeah, it was really good, sir. And I got a lot of information from your presentation.
Thank you.
Your work on various materials, sir. Actually, I work on semiconducting polymers, the donor and acceptor based materials. So, did you ever try to use them in sensors?
Yeah. Already we have developed the polyaniline and polymer materials for the sensing applications like polyaniline and polypyrrole. And so we have observed that that is polymer basically is used for the ammonia sensors.
Yes.
And just these devices I have explored. So these are the polymer sensors, ammonia sensors.
In addition to that, sir,
most of the works we are presently doing
on
the polyaniline and polypyrrole based sensors.
Yeah, okay. Previously, even I had gone through your paper also, sir, which you published in Sensors and Actuators.
Yeah.
On tungsten oxide based sensor also.
Right.
It is really informative for me, sir. So I wanted to. I usually work on semiconducting polymers like benzodiazepine and donors as well as the diketopyrrole based acceptors. So I was just curious, sir, whether we can use the process which you developed for those kind of polymers.
Okay. Basically, we have developed the polymers by, for example, polymer. Polyaniline is one. So we have developed polyaniline by using aniline as a monomer.
Okay,
by simple chemical oxidative polymerization method.
Yes, sir.
The aniline is a monomer we have used. We have used the HCl and we have the catalyst and ammonium persulfate as an oxidant.
Yes, sir.
Okay, in a proper manner, that is 1:1. Basic 1:1 ratio. We have adjusted aniline as 1 and if it's 1:1, 1:0.5. We have varied the combination and initially generally conducting polymers. They are conducting one generally.
Yes, sir.
Polyaniline. Okay, so for making the semiconducting, there is a need of the de-doping. So initially, polyaniline is a conducting form. And after that, we have added ammonia.
Okay.
There is de-doping, you can say that. Okay. So 0.1 more ammonia we have added into the conducting polyaniline because for gassing applications, the semiconducting materials are used. That we have de-doped this polyaniline. Okay. and we will get a semiconductor poly analysis.
Yes, sir.
This is very simple. We have published this sensor, polyaniline based sensor in the metal chemistry C.
Okay, sir. Yeah.
So you will find there the various process of the polyaniline. Similar kind of the polymer,
Okay, sir.
polypyrrole we have developed. So in that case, we have taken a pyrolyzer monomer, and same thing here, the HCl and APS as oxidant, because we have tested the other oxidant also, that is the perichloride and other also. But we found that the APS, ammonium sulfate, is a very good oxidant, and we'll get a very good form of the polypyrrole.
Okay, sir.
So, and we have used the polypyrrole for the gas sensing applications.
Okay, sir. So thank you so much, sir. Thank you so much for the explanation.
Thank you, sir. And I welcome Dr. Bhatula, sir. Now I request our honorable principal and president of inaugural ceremony, Professor S.M. Mulani, sir, for his presidential address. Professor S.M. Mulani, sir.
Am I audible?
Yes, sir.
Yes, sir, you are audible.
Good morning to all of you. Distinguished keynote speaker, Professor Dr. Vikas Patil, ex-Provici, Punyashlok Ahilyadevi Holkar, University Solapur, present IQAC coordinator, Punyashlok Ahilyadevi Holkar, Dr. Bhagwan Navle, Head Department of Physics, Dr. Shankar Dasade, IQAC coordinator, Dr. Jagannath Thombre, convener RTNA 2023, Mr. Ashok Kamble, sir, and Dr. D.K. Bandgar, sir, member of organizing committee. Most valuable resource person, C. Bathula from South Korea, Dr. Yashi from US, scientific research, and staff. It's my great pleasure to welcome all of you on Zoom meeting platform for international e-conference on recent trends in nanomaterial and its application, that is RTNA 2023. This conference is held between and 23. Very much interested in the material information in the space and how is to be changed. In the space, changes may occur due to some temperature effects. Some other parameters like speed of wind, rate of formation of cloud, and raining will start at particular season. All these changes in the environment may occur because of only material formation in space. So, formation of material and its preparation in various sizes plays an important role in our daily routine. Our keynote speaker, my best friend, Honorable Professor Vikas Patil sir, has explained the synthesis of nanomaterial and its uses in various applications. I hope that all participants will enjoy this conference and actively participate in the valuation with resource person. Some undergraduate and postgraduate students are also participated in this conference. I hope that this conference will be too much benefited as your basics in research is concerned. Every participant will enjoy RTNA 2023. Wish you all the best. Thank you.
Thank you, sir, for your presidential remark. Now I request Dr. B.B. Navle, Head, Department of Physics, to pay vote of thanks of inaugural ceremony. Dr. B.B. Navle, it's over to you.
Okay, I am audible?
Yes, sir.
Okay. Welcome all of you. On behalf of International E-Conference on recent trends in nanomaterials and its applications, I take this opportunity to propose vote of thanks. At the outset, I thank our resource person of this inauguration function, Professor Dr. B.B. Patil from Punyashlok Ahilyabai Holkar, Solapur University, Solapur, for giving exact knowledge about top-down, top-up approaches, supercapacitors, nanotubes, gas sensors in nanomaterials and its applications. We are really enlightened with your knowledge, sir, and presence. We are thankful to our honorable president of this inauguration function, Principal respected Dr. S.M. Mulani, sir, for their motivation and enthusiastic support for this great event. A special thanks to our convener of this conference, who is intelligence, faculty, and ex-student of this college, Dr. J.V. Thomre, sir, for arranging such a great event. And our heartfelt thanks to IQAC coordinator, Dr. S.S. Dasade, sir, Professor A.M. Kamle, sir, then Dr. Dada Sobandgar, and Raju Sadegle for their active participation for arranging such a great event. Finally, I wish to express my sincere appreciations to all participants which are now present here. Thank you once again. Thank you, sir.
Thank you all of you for being with us. I declare, with permission of organizer, the inaugural function is over. Now we will start.
Thank you very much.
Now we will start session second. Once again, I welcome all in session second. In session second, we have resource person Dr. C.D. Batula from Dongguk University, South Korea, and chairperson of the session is Dr. P.A. Bansode. So Dr. P.A. Bansode, currently he is working as associate professor in chemistry at Sangola College, Sangola. He completed his BSc from Shivaji University, Kolhapur as a gold medalist. He completed his MSc in organic chemistry from University of Mumbai. He has received a PhD degree from Shivaji University, Kolhapur, and title of PhD thesis is Synthetic Studies in New Anti-Cancer Therapeutics. In addition to this, he qualified NET, SET, and GATE examinations. He is having a teaching experience of 16 years. As far as his research is concerned, he has published 30 research articles in well-reputed national and international journals. Also, he has granted 3 patents in his credit. He is a Best Paper Awardee for cancer research in various international conferences. He has worked as a resource person, chairperson at various national and international conferences. He received Brand Kolhapur Award, Best Teacher Award, and Best Researcher Award. He delivered many guest lectures on various topics, and he has completed minor research project funded by DST SCRB. With this brief introduction, I welcome Dr. P.A. Bansode, sir. Dr. P.A. Bansode, sir, it's over to you. Thank you.
Thank you. Thank you very much, Dr. J.V. Thomre, sir. Am I audible?
Yes, sir, it's audible.
Okay. Thank you very much for a very nice introduction of mine. I'm very much thankful to the organizers, Principal Dr. S.M. Mulani, sir, Dr. B.B. Navle, sir, Head of Physics Department, Dr. Shankar Dasade sir, IQAC Coordinator, and Dr. J.V. Tombre sir, convener of this international conference, for giving me opportunity for chairing this session. For the second session, we have with us Dr. China D. Bathula as the resource person. It's my great pleasure to introduce Dr. C.D. Bathula. He has completed his BS in chemistry and masters in organic chemistry from Karnataka University, Dharwad, Karnataka, India. He also completed his PhD in the subject of organic chemistry from the same university. The title of his PhD was Studies on Synthesis of Bis-benzimidazole Derivatives. He also worked as guest faculty in the same department. Then he has industrial experience working with SAMI Labs as a scientist in synthetic organic chemistry division in Bangalore, India. He has long-term experience as a postdoctoral scientist. He has worked as postdoctoral scientist in the field of organic solar cells in the Korea Research Institute of Chemical Technology, Daejeon, South Korea, between 2010 to 2013. He has also worked as postdoctoral scientist in Institute of Nanoscience and Technology, Hanyang University, Seoul, South Korea, between 2013 to 2016. He has also worked as postdoctoral scientist, Eva Women's University, Seoul, South Korea, in 2016 to 17. And still, he is working as assistant professor, as told earlier. He has the area of expertise as organic electronics, OLEDs, organic thin film transistors, organic photovoltaics, dye-sensitized solar cells, perovskite, hybrid materials, sensors, energy storage materials, environmental chemistry. Hence, he has hands-on experience in total synthesis and chiral synthesis of bulk drugs and fine chemicals. He has also worked in the field of microwave-induced synthesis for the antibacterial, antifungal, benzimidazole-based compounds. He was awarded with a research fellowship for his doctoral research between 2003 to 2007. He is the member of Korean Chemical Society since 2010 and member of Polymer Society of Korea since 2011. Regarding his publications, he has published 115 research papers. So this is the big number, 115 research papers in various reputed peer-reviewed international journals, and his H index is 21. With this brief introduction, I heartily welcome Dr. C.D. Bathula sir in the second technical session of this international e-conference. Welcome, sir, and over to you, Dr. C.D. Bathula sir.
Thank you, sir. Thank you so much, Bansode sir, for introducing me, and also I would like to thank all the organizers, especially the Jamboree sir, as well as each and every organizers, as well as the chair of this session, and Patil sir, who has presented, who gave the very nice presentation on the nanomaterials, and which has made my job very easier. And especially, I just want to connect it to the undergraduate colleges in India, because that is the place where the science starts, and that is the place where we need good encouragement as well as the good guidance, from where we can make a good scientist as well as a good contributors for this society. And I would like to thank once again everyone. With this, I just want to start my presentation on organic materials for the optoelectronics, energy, and environmental applications. My talk will be consisting of the introduction and summary of research work, and I will focus on some solar cells, photodiodes, energy storage. Already Patil sir has spoken about this, so I'll just try to shed some light on it. And also, I would like to share the information about some opportunities in South Korea, and acknowledgements. So my screen is visible, right?
Yes, sir, it's visible.
Okay. Yeah, this is how the most of the faculty members of the Sangola College know about how the Korea looks, as well as the how to reach it. This is how we can reach the Korea. This is southern part. Even I belong to southern part of India. So to reach Seoul, either you can go via Hong Kong or via Singapore. And these are some of the pictures from the Korea. Since there's a lot of research on electronic materials, organic as well as inorganic materials. So I just took some pictures. This is the called as a Lotte Tower. It's around 120 floors, and as well as this is the iconic Seoul Tower or Namsan Tower, and this is the this is how it looks during the cherry blossom. And this is the school or the university where I presently work. This is called a Donguk University, Seoul. And these are the 4 seasons of Korea. Then, in autumn, the every leaf converts into like a uh, colorful thing, as well as in spring or in cherry blossom, you can see every leaf becomes the flower. And coming to the my work, actually, as the sir introduced, I worked on organic semiconductors. So why most of the people work on the organic semiconductors in Korea is here the research is funded by the government as well as the companies like the LG and Samsung, who are the very big players in display as well as in electronics, mobile phones, or any. If in even in current situation in our home back home in India, everyone, any family you see, they'll have at least one product from the Samsung. Either it may be refrigerator, television, or mobile, because there is a lot of funding for the organic electronics materials, and whatever the research output or promising results you get, that will be taken by the R&D section of the Samsung and the LG, and they develop it, and it will be useful, immediately useful. And this is one of the solar cell summary which I wanted to show how it started and where exactly now it is. You can see that this is the pretty old one. If you see the recent one, the Korea is almost sitting on the top of the solar cell research. As I said, the reason is there is a lot of funding as well as the lot of contribution comes from the our Indian researchers who are working here in various disciplines, either from the synthesis or the device fabrication. There are a lot of researchers from our country, especially from southern part of our country, from Karnataka, Maharashtra, Tamil Nadu, Kerala, and even other parts. But southern part is contributing more for the universities, as our researchers have been skilled in synthesis as well as the device fabrication. And this is the brief history how the OLEDs have been the revolution of the OLED has been taken place. If you see the early 1950s from the Japanese laboratories, you can see that every 10 years there is a progress, and there are many people who achieved Nobel prizes in this field, such as Professor Alan Heeger in 1980, as well as the Professor Heeger also and Professor. There are so many researchers who received the Nobel Prize in which on organic electronic based materials such as the OLEDs as well as the displays. And as I said, Samsung Galaxy as well as LG, they are very big players because they make very large screens, and the results have been reproducible. Also, have been approved by the NREL Laboratories USA. This is the organic photovoltaics device structure, and maybe there may be many students also who may be very curious when they see this kind of structures. No need to worry, as the faculty members already know about this kind of devices and everything. But in case of the students, when they see these kind of structures, they might be initially they may be very curious, like how to make this kind of devices. And I want to advise to students that once when you come enter in electronic laboratory, there is a space, there is a time to learn the things. So no need to worry when you try the many devices, and you can learn and you can come up with the good results. And as I said, every expert is a once a beginner. When I see the Professor Patil's presentations, when he presented from the tungsten oxides to all the nanomaterials as well as the polymers also he used. That is very interesting for my part, because most of the I am actually I worked on many polymers, so even the strategy I'm going to use in the future also. This is called as the normal solar cell structure, and this is the inverted structure. Here we have the substrates, then we coat the period pieces layer, and these active materials we are making in the laboratory, and other evaporations are done by the thermal evaporation method. This is very controlled. And as I said, we worked on organic polymers. This is how we started our journey by making one of the promising triisopropyl containing molecule, starting from the, even this moiety is prepared from the thiophenol carboxylic acid. I didn't put the background of this reaction because we already prepared this material and then used for this reaction. Why we are using the triisopropyl silyl group? As I told, electronics need to be done by roll-to-roll processing or the screen printing or by 3D printing. In this case, solubility is very important. When the moiety is very rigid, the solubility becomes difficult, and also processing. Processing is very, very important when it comes to organic material. Whereas in case of the inorganic materials, as sir has presented, we grow them on the directly on the substrate also. But here the film quality is very, very important to get the promising properties. So we, by synthesizing this molecule, and then we prepare the polymers also. For preparing the polymers, we have prepared the monomers. How we prepare the monomers? As I said, we started from the thiophenol, and by when we done the 5-step reactions, and we got this kind of thiophenol based derivatives. For every student, I want to tell that this is the everything is the fundamentals of the chemistry as well as the fundamentals of this science. We are just like Friedel-Crafts acylation, then chloromethylation, cyclization. These all things you might have read in your textbooks during your undergraduate studies. And the same things we are doing in the laboratory with the utmost care. That's what, when you start the experiments, it's very important for all the researchers to be work in the safe environment, and also have a thorough group discussion, as well as you read about the materials which you are handling, and this way you can make the promising materials. So as I said, we introduced different kind of heteroatoms also, like halogens also we introduced into the same kind of moiety. Here you can see that the reaction sequence is same, but some reactions are very challenging. By using the butyl lithium, lithium is highly flammable. So how to use this kind of reagents? You can learn with the help of your seniors, as well as the uh, you can take help of your group members to handle such kind of reagents. And even though this looks a complicated kind of structure, when you perform each step, yeah, when you characterize the material, yeah, you will be happy, because the whatever the things you read in the book, or whatever the things you understood, its mechanism you are doing in the practical way. So this is another ester we prepared by same methodology. And the polymerization is done by this is called as a palladium catalyzed stille coupling reaction. The stille is when the organic tin compound and the organic halide compounds are coupled in presence of the palladium catalyst. It's called a stille coupling reaction. Whereas if you have a boronic acid here, it is called as Suzuki coupling reaction. These reactions are very important these days to make a directly CC bond. And this synthesis is not only just for the polymers, and also for the small molecules. Whenever we have coupling reactions, we use this kind of molecules. and prepare this kind of polymers. And these are the analytical properties or electronic properties by UV spectra. The liquids UV, when you take this in solution and the solvent and the solid, you can clearly see that there is a pi to pi star transition, and also there is a good packing. Whereas in case of the liquid, there is the molecules are in dilute condition and they're fragile. Whereas in case of the solid UV spectra, the molecules are closely packed. And the DFT studies is very important to understand the orbital concept, as well as the to support our hypothesis or support our experimental data. DFT studies have become very important to increase the impact of the work. And this is the solar cell measurement data. And as I said, for the students, these are machine generated. To get this kind of data, you should make a good device. So once if you make a device, you need to try until you become expert in making a very good device. And slowly and surely you'll become a good device physicist also. This is the as I said, the surface surface is very important for organic devices. This is we studied the surface phenomena by AFM, whereas for the inorganic materials we usually take the SEM as well as the PEM. You can see that when you add some additive to the devices, the film morphology improves, or the smoothness you will get, and thereby increasing the efficiency of the device. And this is the transistors. Transistors also made in a different in different structures. One is the top contact, and the bottom contact morphology. Some laboratory, depending on the laboratory conditions, they use the device organization and then get the good mobility. As I said, we developed this moiety for the first time, and then we have done various polymers to see how the properties are how the properties are changing with respect to the acceptor molecule. And why we worked on this molecule? This molecule is being developed by Professor Yang group in California in the year 2009. It was a same time we were also working in the molecule. Purification of this molecule was very challenging, but we were successful in preparing this molecule in the laboratory, and we prepare this molecule and with a high purity. This is the highly fluorescent material. This is called as diketo pyrrolopyral molecule. As polypyrroles has been also used in the energy storage. Even this material also is been used in the energy storage application. And as I said, we worked on a lot on the organic structures with the different orientation. This is called as zigzag structure, and this is called as the normal structure. Normal structure, you can say it's a planar, whereas in case of zigzag structure, the strategy changes. We have to start from the first step itself. We have to take we have to select the core. This is done by the retrosynthetic analysis. Retrosynthetic is nothing but the reverse strategy for the synthesis. So we started with the naphthol. This is called an alkylation reaction, which most of you might have studied. And this is bromination, and this is sulfonation. This is cyclization reaction. And all these reactions have been done in the laboratory, and we got a very pure monomers. Then we use for the polymerization. And as I said, we always compare the impact of the the halogens on the backbone of the polymers by and we make the device, and we come up with the conclusion that halogens are playing the major role in enhancing the device performance as well as the mobility. And as I said, this is a TGA, thermogravimetric analysis, as most of you know about this. If we want to use some material for the devices, it should be stable, so that it can be used in a large scale, as well as even in the open atmosphere it can be kept. As we see in some places, the temperature in some parts of countries 40 or 45 degrees, we should make sure that some device if you make, it should be stable for any humid condition as well as the high temperature. So when we take the TJ, we can see that the molecule is stable up to 300 degrees Celsius. So it can be, we can use freely use in the device, and the device will be stable. And this is the transfer characteristics for the TFT we prepared. And as I said, DFT is very important for supporting our hypothesis. And this is the AFM images showing the surface morphology. Yeah, the solar cell properties also we have studied, and we show this the structure gave the better efficiency compared to the normal structure. And we compare this of the photophysical properties also, UV as well as CV, and also prepare the transfer curves, the transistors. And finally, we arrived at conclusion that the zigzag is much better than the normal structure. But the synthesis of the zigzag is very challenging, but it's possible. As I said, we always start with the thiophene, and we try to prepare this kind of we try to construct this kind of the molecules which are useful. And in one of our moiety, we introduced the silane. Why we introduced the silane? Silane, it's very important to get the single crystalline materials. In small molecules, we can do the crystallization, sublimation, or recrystallization, and then we can get a single crystal. But in case of polymers, it's quite challenging. So we introduced the silane, and we got the single crystalline material. And the inverted solar cells, as I told you in the introduction, we prepared this material in the laboratory, and this we had a commercial one, but later on we replaced this fullerene derivative also, and this dye also we prepared in the laboratory. How we prepare the dyes? You can see that every step is a challenging, but we got a material with the high purity. In the first step, we prepared the boronate, and then here we have done the alkylation and the formylation, and this is called, as I said, Suzuki coupling reaction to get the boronate, the coupling of the boronate and the bromo, and we got aldehyde molecule. In case of the students, no need to worry about this kind of structures, especially if you make the simple molecules, or the chemistry will be same, the fundamentals of chemistry will be same. So no need to think much about this, but you can get the one. There is the functional group transformation. Aldehyde is converted into its cyanoacid acid derivative. These are useful in the dye-sensitized solar cell. And as I said, the silane gave the single crystalline. When in case of the XRD of this kind of polymers, the 2D the values we get below 5 degrees. When you get below 5 degrees, it's very difficult to do it by normal XRD. So we go to the synchrotron facilities, which we have in the southern part of Korea, and we go there, and we, with the help of the experts, we get this data. Otherwise, it's difficult to get the data by normal XRD measurements. And normal quinoxylines also we have prepared by using the benzyl derivative. So when you tune the properties of any molecules, it is important to use the various kind of alkyl groups. Alkyl group also have very more effect on the organic polymers, and also their properties. So we have done the reduced by using the BT, benzothioindazole molecule. We open the ring to get a diamine. Then this is simple quinoxylene construction. To have another spacer, pi spacer, we have done introduced the thiophene by the Stille coupling reaction. And yeah, these are some of the chiral molecules. The reason why I want to show this is recently a lot of chiral molecules have been explored in the perovskite solar cells. Since they have even the CPL instrument, with that they can also see the configuration of the material. This has been even very useful in the chemical drug industries also. As I said, the protection as well as the esterification and reduction, as well as the cyclization. These are all the basic reactions finally we can get this kind of molecules, and this can be used in organic pharmaceutical industries for as a drug intermediates, as well as the in solar cell for passivation. This is the similar kind of molecule. The stereochemistry, how we can invert the stereochemistry. Here you can see that in one of the molecule, we started with the 2s and 4s, whereas we ended with the 4r and 2s. So we can reverse the stereochemistry also by using the various steps. And as I said, in case of the polymers, we can improve the properties by extending the pi conjugation. Here, when we have done many of these kind of polymers, but to increase the its efficiency, we used the conjugated material, this pyrene, and we got a promising properties. Actually, we tuned from 2.5 to 10%, and in case of the 5%, we got a very good results. Here you can see all the properties it's been shown in this slide. And again, the AFM, is clearly showing that when we use the 5% of the material, the additive, the morphology is better. And these are the thin film transistor we prepared for the, this is called as the random copolymers, or using the third component into the polymer backbone. So here we studied all the optoelectronic properties, and the interesting thing in this was when we use this the pristine material, and when we add the other component, the mobility has been increased. So this is the concept-based results rather than the high mobility. This kind of concept we can use for other materials, and we can tune up the properties. And this is the DFT studies as well as the surface analysis. And the transistor, we have prepared the transistors by the device structure like this, by encoding the semiconductors, the dielectrics, and then also the gate. At various voltage, we have studied the, we have seen the transfer curves as well as the mobility values we have been summarized. And in addition to the transistors, we also worked on the photodiodes. In case of all these devices, the materials change to a certain extent, but the fundamental materials remain same, such as the acceptor, we can replace it. Even the polymers, we can replace it, the acceptor as well as the donors. Here, the device structure I have shown in the first slide, like how it works. In case of the photodiode, we measure by biasing. When we measure the EQV, we need to bias the voltage. Since this is the material was showing the absorption around 700, this is not exactly near IR, but NIR 2 you can say, because around 750 or 800. But we developed the materials which can show the diode performance at around 1000 nanometer also. And this is one of the, as I said, we work on the OLEDs. How we can publish the high impact factor in OLEDs as well as the commercialization point of view also. If you want to make a good OLEDs, what are the slides I have shown in the previously, that involves very challenging synthesis, but whereas this kind of synthesis very we can perform in the laboratory easily. So as Patil sir has developed many processes inside the laboratory, and even any of the researchers, they can, even the master students or the researchers, they can handle it, and they can produce the results, reproducible results. And this is also similar concept, because here this is a multi-component reaction, and we use the bowel milling as the green synthetic protocol. And one more thing is halogen-free solvent. As we said, we talk a lot about the environmental pollution as well as the environment-friendly solvents. So green solvents are very, very important to avoid the toxic chemicals. So for these molecules, we studied the DFT, the energy levels, and this is the device structure, how we prepared. As I said, all the molecules, some of the molecules we got commercially, and some of them, like IR iridium-based complex, we prepared in the laboratory. And all these measurements are, we have prepared the devices and done the measurements in the clean room. And this is the device performance. You can see that the these are simple cores. These molecules are very simple imidazole cores, but they are very promising, and the results were very promising, and we could publish that in a good journal. And uh, as I spoke about the green synthetic methodology, we can use this kind of methodology to many metal oxides also. Especially some copper-based materials we can make by green synthesis by just by manually grinding, as well as we can introduce this kind of material into the toluene and heat it for a few hours, and then we get the transparent solid crystals. So this is how we prepare the material. You can see that we ground it and then heat it in the even the vial, sample vial, and we got this kind of materials, the transparent the crystals, which become the fluorescent when you shed UV light on that. And these are the different properties we studied for the materials: the XRD, TGA, DSC, as well as the IR, the XPS, to understand the individual components of uh, the material. And these are the different device parameters where how we measured the OLED properties, and we prepared white OLED with this. And the contact angle measurements are also very important for us, as well as the surface properties. And perovskite materials I wanted to introduce to the especially for the students. As there is there is a lot of research in the perovskite materials, because they are become very promising, as the efficiency is very high, but still stability is the problem. So to overcome such a problem, we are making this perovskite materials on the clays such as the halloysite, colonite, and other clays. How we are making this is by very simple strategy, by taking the precursors and clay we are studying in the DMF, followed by adding the anti-solvent, and we get such kind of beautiful colored material. We study all the optoelectronic properties for these molecules also. And here the SEM and TEM has been measured. It clearly show that the molecule, the perovskite materials is clearly binding to the surface of the clay. And this is another green protocol. As I said, by simply by grinding, we can get the perovskite materials. But we need to improve this methodology still, because manual there will be some errors. But to overcome this, we have done this by using ball milling also. The characterization has been done, as well as the optical properties we studied. And yeah, as some of the work we done on the energy storage also, like zinc oxide materials, and we worked it on environment friendly cellulose nanofibers. We developed these nanoparticles on the cellulose nanofiber. You can see that cellulose, it is nicely decorated on the cellulose nanofibers, and the material has been well characterized, as well as we prepared the supercapacitors for this kind of materials. And this work was published in JMCA. The basic thing is exploring the cellulose nanofibers has been very it was promising for this concept. And again, as I said, hydrothermal reactions also we have done for some of our applications for energy storage. For everything you need a good characterization data if you want to publish in a very good paper, such as even the XPS, as well as how the SEM and TEM, how to arrange the figures are very important. This is the information is just for the students who are looking forward to have their career in the research. And yeah, we also had we published this paper in the energy storage. And as I previously said, CNT and the polymer, how to have a good phytoplaster interaction. So this we have done it by ultrasonic exfoliation, by simply by this polymer we prepared in our laboratory, and also with this CNT. With that we prepared a very nice morphology, we can see, and we prepared also the supercapacitors and we propose the mechanism as I was discussing with the Patil sir about this. Some of our materials we work on the semiconducting polymers, so we wanted to use these materials in the energy storage as well as the sensors. So how we also worked on some materials on the graphitic carbon nitride. Even this was a very interesting work, since this is done by green synthetic methodology, as well as the here we have done the multiple applications. We got the energy storage as well as the environment. Sir, how much time I have, sir?
Sir, it may be 20 minutes.
Okay, sir. Okay, thank you, sir. So yeah, already as sir has spoken about the energy storage, so I won't be talking much on this. This work we could publish in the hazardous materials, as we have done multiple applications for these composites. And this is I wanted to also shed light on the degradation experiments. How to prepare the simple materials by the ultrasonic methods. Here we have very natural sources, since most of us from the southern part of India, we have very big natural resources. How to use them for the environmental remediation? We can make the biocarbon, or we can make the activated carbon from that, and we can uh, prepare its composite with the bulk materials, or we can make some polymers also, and we can have the sheets, carbon sheets, and by characterizing this kind of materials by the XRD as well as the SEM as well as STEM, we take it for the dye degradation. Dye degradation is very important, especially for us who have the water scarcity in some of our places, and we need to find a solution for the since the Indian government also have the plan. It's called a Swachh Bharat mission they had. So how to make it? It should start from the every corner of our country and every corner of our province, the southern province of our country. So when we use this kind of carbon, have very good absorption property, and this increases the degradation of the dye. And these are some of the things I wanted to share with the students, like opportunities in Korea. Like these are some of the opportunities for the students as well as the faculty in Korea. This is how the Korea looks. This is Seoul where I stay. Even my friend and colleague, Professor Sagar Mane, also we work together in the same school. Yeah, this is how it looks. Korea is full of universities and a lot of for the faculty as well as the students. And this is some of the universities in Korea, such as the Seoul National University. This is the topmost in Korea, as well as it comes under top 30 or top 50 universities of world, especially. The departments are very good, and they have a lot of funding also. And some students who are looking forward to for such kind of enter such kind of universities are requested to go through the websites. And this is how the university and the campus looks. Just the infrastructure is great, as well as they have more facilities. The reason is, since they have to pay a lot of tax to the government, instead of paying the tax to the government, they give the funding to the universities. So this is the Yonsei University. This is the top second university in Korea. Here also you can get the admission. Students who are looking forward for the either master or sites, and before applying everything, the thing is you have to interact with the Indian community over there. There are a lot of Indians, especially southern India, either from the Karnataka or Maharashtra. You will find a lot of people. Interact with them about the opportunities, and also then try to get the information about the host professors, universities, fellowship, and everything. You should come here with a good fellowship. You should not be depend on your family for the further studies, because it's already a big burden for them. So there are many fellowships in these kind of universities, and even I'll be in contact with Manis sir as well as Jambare sir. Like if you need any information on these universities, I can provide the students. And it's very these some of the departments of these universities are topmost in the world. Also, you can see the top 10 material science and engineering department in KAIST is top in the world. And this is the fellowship for the faculty as well as the postdocs. And there is the University of Science and Technology, which also gave the good fellowships. There are many institutes under this university. And in UST, you can get the fellowship also. And the most important thing is you try to get the IELTS examination. As I said, everyone cannot be the good in communication, but there is always chance to improve the communication. Talk to your faculty, talk to your seniors and everything. Try to improve your communication skill as well as the get the examination. And most important thing is we need to help one another to achieve the success. And there are good government scholarships in Korea also. You just try about these fellowships. And there are some green talent fellowship from the Germany where you can get a good scholarship also. Some of the people some of the students who are doing the PhD or a master, they can also visit to Germany on green talent. This is for 3 months, and they'll take care of you and they'll pay you your airfare as well as your stay. And the global scholarships in Australia, there will be Professor Mahesh Suravanshi will be talking tomorrow. I think he can help you with this information also. And this is some of the devices on the photo detector. Already I have discussed this kind of studies in my previous slides, so I'm going to skip these things. And most important thing is we have to be, if you're humble, nothing will touch you, either praise, neither disgrace, because you know what you are. So we have to work hard, have to help each other. And especially I would like to thank the teachers, because most of the teachers who are in the teaching us in the undergraduates at level, they get, I'm not sure what kind of, what quality of student they get, because most of the students who want to go for engineering, they go to the engineering. Maybe the students with the basic fundamental, they come to the basic science, and that is where most of the teachers are playing major role and making good researchers, good scientists, and good educationists and good entrepreneurs and everything. And one of the most important thing I like it, until and unless you do the hard work, you cannot become successful. That they sow in tears and shall reap in joy, because without hard work, there is no success. I dedicate most of my work to my beloved teacher, Professor I. M. Kaji from the Karnataka University. And I would like to acknowledge help from the Professor S. M. Pawar sir, who is the Dean in the Sanjay Godavat University, Professor Abhijit Kadam, Wilson College, Mumbai, as well as the Professor Lee from the Korea, as well as the Professor Kumbar from USA. And I have my mentor from the Korea also. And I would like to thank Professor Sagar Suresh Mani sir, Principal of D.R. Patil College, and Professor Sagar Mani, the Dongguk University. Especially, I would like to thank Professor Tombare sir, who has been kind enough to give me this opportunity to present some of my words. What I say is this may be sometimes this may be confusing for students to which one to pick up from these slides. But what I say is to try if you have any problem, you can contact me through Professor Tombare sir or Professor Mane with my good friend, and I'm here to help you. And I thank you once again all the organizers, and thank you so much, sir.
If participants have any question, then they can ask the question. The session is open for discussion. Sir, I have a question related
Yes, sir.
to polymeric materials.
Yes, sir.
If you are treating inorganic material, then we can say it is a optical, then the direct or indirect type band gap. As far as
Okay.
the polymeric materials are concerned, then how we can judge that band gap, that is homo lumo difference between the, so how?
Homolumo is done by sir, the UV.
Yeah,
By UV, by talk plot, you can get the even the band gap.
yes sir.
But the thing is, by CV, you get the oxidation potential,
Yeah,
and in many polymers, it's difficult to get the reduction potential because once the oxidizes,
yeah,
difficult to get reduced. But on the basis of that, we get the oxidation potential, and we have the equation for calculating the EOMO
yeah,
by using with reference to the ferrocene. There we get the optical the properties like the homolumo by the electrochemistry, as well as the by CV as well as the UV. And even though this is you get some information, but most of the device guys, especially the fundamental device physics, the device physicists, they go with the UPS technique,
yeah,
ultraviolet photoelectron spectroscopy, where the band gap is you get the exact band gap.
yes sir.
So that's and also it is also supported by the DFT studies. We compare all the band gaps, and then we arrive with the we come to a conclusion about the exact band gap.
Yes sir. Dheeraj Kadam.
Yes, sir. I have a question.
Yeah, yeah. Please
Sir,
ask.
I am a research student at Solapur University. Sir,
Okay.
I am doing my work on perovskite solar cell.
Okay.
I have to construct solar cell using polyethylene 2,6 naphthalate and titanium dioxide. My question is, sir, which substrate should I use to get better result?
Substrate. You want to make the flexible one, or you want to make the normal one?
Normal one, sir.
Normal, if you can go with the FTO also.
Okay. Okay, sir.
FTO you can go, or if you want to make the flexible, you go for the PET substrate.
Okay, sir. And sir, which method should I use? Which will be beneficial for me?
Like how I'm not sure. How about the condition of the laboratory? You are
Sir, there is a spin coating technique.
no, the thing is, excuse me. You are doing the fabrication in dry room, or you are doing inside the glow box?
Dry room, sir.
Dry room, right?
Okay.
Oh,
Yes,
okay,
sir.
okay. You can just go with the normal spin coating technique only.
Mm-hmm.
Did you try any time with the TFSI derivatives?
No, sir. I'm just a beginner. Just a beginner, sir.
Okay, fine.
So that's why
yeah. Just go with the. Otherwise, you can go with the compact TiO2.
Okay.
And recently, we can have some small interlayer also over there to overcome the defects. When you see the TiO2, the CM images, there will be some defect, right?
Okay.
To overcome that effect, some of the people, they use copper iodide.
Yes.
So you have a small layer of the copper iodide, maybe around 2 milligram per milliliter concentration.
Okay.
Then you can make a very good device, because that whatever the defects is there inside the TiO2 layer, that barrier you can overcome.
Okay. Sir, will it be successful by using spin coating?
Definitely, it's successful.
Okay. Thank you, sir.
Welcome.
Thank you.
Thank you, sir. So I will conclude. Thank you, Dr. P.A. Bansode, for sharing the session. Now, my sincere thanks goes to Dr. C.D. Vatula, sir, for wonderful presentation on organic materials for electronics, energy and environmental applications. So thank you, sir. Now we will start session third, that is oral presentation. Session third is a oral presentation. Once again, I welcome all in session third, that is oral presentation. The session coordinator is Dr. B.B. Navle, Head Department of Physics. So I request Dr. B.B. Navle, sir, It's over to you, sir.
Okay, sir. I am audible?
Yes, sir.
Okay. Now welcome to session, last session to today's number 3, which is a oral presentation. We have here with this session Dr. S.M. Mane, who is our ex-student from Vidnyan Mahavidyalaya Sangola. He can chair this session. Doctor, it's my great pleasure to introduce Dr. S.M. Mane. He is now working as a research professor, Department of Fiber System Engineering, Yangnam University, South Korea. He was awarded his PhD from Punyashlok Ahilabai Holkar, Solapur University, Solapur. Also, he made his bachelor degree from Vidnyan Mahavidyalaya Sangola, master degree in School of Physical Sciences from Solapur University. That is Punyashlok Ahilabai Holkar, Solapur University, Solapur. Also, he has 3 years project fellow from UGC Major Research Project, Department of Physics, the Institute of Science, Mumbai. He has also worked as an assistant professor at various, that is at Department of Physics, Institute of Science, also in Department of Physics, Anna Sahib Vartak College, Vasai Road, Palghar, Maharashtra. He has also got a postdoctoral fellowship at Department of Physics, Yangnam University, South Korea. So he has a divisional of electronics and electrical engineering, Dongkong University, Seoul at South Korea. He has published a total about 41 papers in international peer-reviewed journals, also in foreign international conference proceeding. Now I hand over this session to Dr. S.M. Mane sir. Over to S.M. Mane sir.
Am I audible? Hello? Hello?
Yes, sir, it's audible.
Sure.
Oh, thank you, sir. Thank you for the nice introduction. I would like to thank the giving me a chance to chair this last session of first day of this International E-Conference RTNA 2023. I would like to thank head of the department, convener, IQAC coordinator and convener of the conference, and the principal of this college. In this session, we have 6 presenters from the different institutions, and each presenter will get 7 minutes. Out of that, 5 minutes are for presentation and 2 minutes are given for the open discussion. So we will start with the presenter 1, who is the can I start, sir? Hello?
Yes, sir.
Yes,
sir.
yes.
Please continue.
The oral presenter number 1 is the Parmeshwar Tanaji Lokhande, who is from the Walchand College of Arts and Science, Solapur. He is going to present his research topic based on the solar light active anidoped barium perichromates synthesized by Soldier method and their excellent photocatalytic activity. I now invite Mr. Parmeshwar Tanaji Lokhande to present his work.
Okay, sir. Thank you. Am I audible, sir?
Yes,
You
it's
are.
audible.
Hello. Okay, sir. Okay. Good afternoon, everyone, and welcome to this e-conference. I am Parmeshwar Lokhande, working as research student in Walchand College of Arts and Science, Solapur. As we gather here today from different regions, I am reminded of the incredible power of technology to connect us and bring us together. It is a privilege to be able to share my research with you today, and I hope that by the end of this presentation, you will leave with new insights and ideas to the ponder. As I began preparing for this talk, I was reminded of a quote by the great inventor Thomas Edison, who once said, "To invent, you need a good imagination and pile of junk." While I wouldn't go so far as to call my research junk, I do believe that it takes a certain level of creativity and imagination to push the boundaries of the knowledge and discover new ideas. So today I want to share with you my own journey of discovery and innovation as I present my paper on solar light active nickel doped barium ferrichromate synthesized by Sol-Gel method and their excellent photocatalytic activity from the initial spark of the idea to the rigorous search processes and finally to the presentation of my findings. I hope to you take you a journey that will inspire you to pursue your own creative pursuit and push the limit of what is possible. I am thankful to the organizing committee to provide me a platform for my research work. So let's look inside the paper. Solar light active nickel doped barium ferrichromate synthesized by Sol-Gel method and their excellent photocatalytic activity. First of all, abstract using various nitrate salts of constituent ions in aqueous solution. We employed relatively novel in the current work to synthesize ultra-fine homogeneous reproducible powder which overcome all the limitation of conventional processes. Here and we synthesize the system BA1 minus X NiXF4 by using Sol-Gel method by changing the concentration of nickel to barium. The structural characterization of the system is its application in photo degradation, and this decoloration and the decoloration of methyl orange are focused to investigation. Thermal examination of form citrate precursor reveals that all the samples under the investigation from spinal phase at the temperature range 650 degrees Celsius temperature. A face-centered cubic spinal structure was formed by well formed, and this will be revealed in the XRD pattern. So in this photocatalytic activity, we reveal that methyl orange dye, which is degraded by the manner 59.45, 60.81, 61.08, 62.16, and 68.04 for the various composition of the X, and very good photocatalytic activity for X is equal to 1.0 after 90 minutes of UV irradiation of the light. The substance with the best photocatalytic performance was NiFeCrO4 and its photocatalytic activity was 68.04. The main objective of this investigation is to determine how synthesized compounds acts as photocatalyst for efficient degradation of methyl orange in the different conditions. In introduction, we know that spinal oxides has a great importance because of their intriguing structure, magnetic and electrical properties, and it also have miniaturized demand for miniaturized material. While it has been found that the properties of ferrites are highly dependent on their synthetic makeup microstructure, which in turn are impacted by the method of preparation. The efficiency of the ferrite device is strong as a result of materials quality. For the ferrite operating at high frequency, high resistivity is crucial to minimize eddy current. So let's look what is the experimental procedure. Chemicals are given here while utilized during this preparation of the compound. Preparation of precursor solution, that means barium nitrate, nickel nitrate, iron nitrate, chromium nitrate is deionized, is dissolved into deionized water separately. Molar ratio are adjusted according to desired composition of final product. Then citric acid are mixed together in a beaker, stirred using magnetic stirrer for 30 minutes, ensure product will form, and stabilizing agent is after that added into that particular solution as a ammonia. Then drying of the gel. The gel is dried at temperature for 6 hours, remove any residual solvent or water. And finally, after confirmation of TGA DTA data, the particular citrate precursor is calcined into the Maple furnace at the temperature range of 650 degrees Celsius temperature for 4 hours. And after that, they are get converted into the metal oxide. Then structural characterization during this presentation, XRD, TGA, DTA, FTIR, same IDEX. These are characterization utilized for this particular compound. In XRD pattern, we reveal that there are the characteristics of diffraction peaks at the 220, 31, 400, 422, 511, 440, 105, and 008 will observe here in this XRD characterization. Spinal structure with cubic symmetry can be confirmed by this 311 peak. Then the spot where it seems the diffraction peak swapped sides higher angle as Ni content increase, indicating the perhaps the lattice parameter has significantly reduced. This observation is consistent with Fagard's law, and this states that solid solution crystallite size varies significantly with composition. In TGA-DTA study, we realized that after 650 degrees Celsius temperature, loss of the weight of the compound is stopped, and during this process, dehydration, citrate breakdown, carbonate decomposition, oxide production are the 4 major processes that occur during this decomposition. At the temperature range 120 degrees Celsius, the peak we reveal that here it is slightly dropped due to loss of residual water. In FTI study, we reveal that the peak ranges are into the 1000 to 1300 per centimeter, and in that particular 120 per centimeter was for the FeO stretching vibration. Then due to stretching vibration of CRO bond is 1150, and due to NiO it was 580. These peaks are observed in FTIR study. Then compound is also analyzed by its morphology and element constituents by using SEM and IDEX technique. In that particular, we know that we can see here the big lump formation will be takes place in the compound, and in the IDEX characterization, we reveal that the percent of the metal and theoretical metal concentration is pretty well matched. Then the photocatalytic activity. In photocatalytic activity, hello sir.
Please conclude.
Hello. Okay, sir. Okay. In conclusion, we realized that we rationally created straightforward, low-cost, novel method for synthesis of compound using sol gel method. Synthesized nanomaterial was used to photodegrade methyl orange when UV visible light illumination was present. According to degradation study, NiFeCrO4 compound shows the good photocatalytic activity. The material photocatalytic activity can be tuned by varying concentration of Ni+2 ions concentration, and it is optimum for Ni+2 concentration. We anticipate that our novel strategy in order to create a mixed metal oxide will create a fresh possibilities for the treatment of the sieve. These are the some references, and thank you. Have a nice day.
Thank you, Mr.
Any question you can ask?
Thank you, Mr. Parmeshwar Lokande, for a nice presentation.
Okay, sir. Thank you.
Participants, so the participants can ask the question if you have any question. If no question, I would like to go to the next presenter.
Thank you, sir.
We'll start with the next presentation from Ms. Gaikwad Swati Sainath. She is going to present present a green approach for synthesis and characterization of nickel oxide nanoparticles mediated by Morus alba plant leaves extract. I will request to Ms. Swati Gaikwad to start her presentation.
Yes, sir. Good afternoon, all of you. Am I audible to all of you?
Yes, yes.
Okay. Okay. Today I explore my presentation on green approach for synthesis and characterization of nickel oxide nanoparticles mediated by Morus alba plant leaves extract. This is the abstract. I have choose a green synthesis method because it is a helpful and it is a simple other than physical method. I have done 3 characterization: XRD, UV, and FTIR. This is nanotechnology. The nanotechnology, the range between the nanomaterial is 1 to 100 nanometers. All of you know about that. Okay. There is some applications of nanotechnology, drug delivery, high biodiversity, target effect, and many more. This is nanoscience. Nanoscience is a material on an ultra small scale. Why I selected nickel oxide? Because nickel oxide are widely used due to their inflammatory and antibacterial properties and its behavior against cancer cells. Okay, next. Introduction of nickel oxide nanoparticles. Metal oxide are crystalline solids that contain cations and metal cations and oxide anions. Nickel oxide is a p-type antiferromagnetic semiconductor with a wide band gap of 3.6 to 4.0 electron volt. This is a structure. I found nickel oxide is a FCC structure by using characterization XRD. There is some properties and there is a nickel oxide nanoparticles as shown in figure. There is some applications of nickel oxide, antifungal, antibacterial, etc. And there is a 2 approaches to synthesize a nanoparticle. I have used a bottom-up approach. Bottom-up approach is a simple other than top-down approach. I use a biosynthesis means green synthesis method. Why I choose the green synthesis method? Because green synthesis is advantageous compared to the chemical and physical methods. It is a non-toxic, pollution-free, environmental friendly, economical, and more sustainable. That's why I use a green synthesis method. There is some advantages of green synthesis method. It is a inexpensive, economic, eco-friendly, non-toxic, etc. And there is a plant. I have used a Morus alba means mulberry plants. They have lots of phytochemicals. Example, alkanoids, flavonoids, phenolic acid, and etc. And this is the schematics of green synthesis of nickel oxide nanoparticle using Morus alba extract. I have used this type of process for making a nickel oxide nanoparticles. There is some characterization techniques, and I have done 3 characterization. First one is X-ray diffraction analysis means XRD. Second one is FTIR. Visible spectroscopy. Okay, first one is X-ray diffraction analysis. From X-ray diffraction analysis, I found crystalline size, lattice parameter, and its structure. This is a X-ray diffraction analysis. This is my characterization. The crystalline structure of nickel oxide is FCC. The lattice parameter of nickel oxide nanoparticle calculated by XRD data is 4.17 angstrom. Crystalline size of nickel oxide nanoparticle is 10.97 nanometer, calculated by Debye-Scherrer formula. Next one, this is the calculations by PIC for PIC. For plane 111, I found crystalline size is a 10.58 nanometer. For plane 200, I found crystalline size is a 8.55 nanometer. For plane 220, I found crystalline size 10.42 nanometer. For plane 311, its crystalline size 14.35 nanometer, and average crystalline size is 10.97 nanometer. Okay, this is a table for XRD calculations, peak-wise calculations, full width, half maxima, D-spacing, grain size, according to HKL planes. And second characterization is FTIR, means Fourier transform infrared spectroscopy. By using this characterization, I found various types of functional groups, and the peak at 523 centimeter inverse were assigned to be a metal oxygen stretching frequencies related to nickel oxide. Okay. There is a table from Fourier transform infrared spectroscopy according to wave numbers, and there is bond and functional groups. And my metal oxide is a nickel oxide found to be 523 centimeter inverse. And third one is a UV visible spectroscopy. By using this characterization, I calculated band gap. UV visible spectroscopy, this is a characterization. The UV visible absorption spectrum, the nickel oxide nanoparticle, the energy band gap found to be 3.70 by using tau plot. And this is a higher other than the bulk band gap, because bulk band gap of nickel oxide is a 3.65, and absorption spectrum of nickel oxide is higher because of due to their quantum size effect. And there is a conclusion. Nickel oxide nanoparticle have been successfully synthesized by green synthesis method using nickel nitrate. And I have done 3 characterization XRD and found to be crystalline size of nickel oxide nanoparticle 10.97 nanometer, UV visible bulk band gap of nickel oxide, which is a 3.65 nanometer, and FTIR spectroscopy, the peak at 523 centimeter inverse were assigned to be metal oxygen stretching frequencies related to nickel oxide. An acknowledgement. Thanks to our college principal, Dr. K.S. Pushare, for providing support, and our departmental HOD sir, A.B. Gavande sir, and supporting sir Gulab sir, and staff Pawar ma'am, Chaitali Pawar ma'am, Naneshwari Pawar ma'am, and Aher ma'am. And thanks to my colleagues. And this is references that I use for preparing nickel oxide nanoparticle. Thank you. Thanks to all of you.
Thank you, Ms. Swati Gaikor, for a nice presentation on the green approach for the synthesis of nickel oxide nanoparticles. Now I request participants to ask the question, if you have any question. If you don't have a question, I have one question. Can I ask?
Yes,
hello?
Sir.
You synthesized this nickel oxide by the green approach, and
Yes, sir.
but I wonder about the application part, where you are going to apply this nickel oxide nanoparticles.
Sorry, sir. Can you please again ask your question?
I just want to ask about the application of these nickel oxide nanoparticles.
It is antibacterial applications.
Okay.
Uh,
Okay. Thank you for the nice presentation.
Okay, thank you, sir.
Now I request the next participant, Sheikh Shabanaz Aminuddin, to present our research topic, that is beta vulgaris plant extract, phytochemical stabilized synthesis and characterization of nickel oxide nanoparticles. Sheikh Shabanaz.
Hello, Manu sir. How many participants are there?
6 participants are there.
Okay, ठीक है.
Please be fast. Hello.
Yes, sir.
Please start.
Yes. Good afternoon, everyone. Am I audible to everyone?
Yes, yes.
Okay. So I am Sabana Sheikh from KSKW Sidco, Nasik. I am MSc students. I have done my research work on beta vulgaris plant extract, phytochemical stabilized synthesis and characterization of nickel oxide nanoparticles. So this is the abstract of my research work. I have synthesized the nickel oxide nanoparticles by using green synthesis method, because green synthesis is cost effective, non-toxic, and it is eco-friendly, and it does not require any high temperature or pressure for synthesis. And the nickel oxide nanoparticles are characterized using 3 different techniques such as XRD, X-ray diffraction, FTIR, and UV visible spectroscopy. So nanoscience and nanotechnology. So nano means extremely small, and nanoscience is the knowledge we are acquiring about material at the nanoscale range, which is 1 to 100 nanometer. And nanotechnology is the application of that knowledge to fulfill our basic needs. These are the example of how small 1 nanometer is. So 1 nanometer is a billionth of a meter, as you can see in the above example. So why nanoscience and nanotechnology is important? Because the material behave differently at nano scale. It have different properties like physical, chemical, and electronical. That's why nanoscience and nanotechnology are important. So these are the application of nanotechnology, such as nano devices, optical engineering, bioengineering, energy, and etc. So introduction to nickel oxide. Nickel oxide is a p-type semiconductor and have a good thermal and chemical stability, and it crystal structures is FCC, and it has a various applications such as nickel plating, nickel catalyst, so lithium ion batteries, solar cell, etc. So these are the physical properties of nickel oxide, such as appearance, critical temperature, density, melting point, boiling point, band gap, electrical resistivity, thermal conductivity. And these are the chemical properties such as IUPAC name, molecular weight, atomic number, atomic mass number. The application of nickel oxides in semiconductors, capacitor inductor devices, batteries, micro super capacitors. So my plant is beetroot, scientific name is beta vulgaris, and there are the scientific classification of my plant such as kingdom, order, family, genus, species. The health benefit of beetroot are as follows. So the phytochemical present in my plant are betalion, flavonoids, polyphenols, inorganic nitric, ascorbic acid, and carotenoids. So this is the schematic of my research work. First, I take 20 grams of beetroot, then I have grind it and I made a juice of it, as you can see in the picture. And after filtration process, I made a extract. And after that, I take nickel nitrate solution and dissolve in distilled water. And after that, I mix both extract and chemical and stir for 2 hours at 70 degrees Celsius. And after addition of NaOH, I maintain the pH. And last, I centrifuge the solution, and cancellation process is done for 2 hours. And finally, the nickel oxide nanoparticles are formed. So there are 2 methods of synthesis of nickel oxide nanoparticles, such as top-down and bottom-up approaches. So synthesis of nanomaterials are physical method, chemical method, and biological method. So I choose biological method. In that, I have done green synthesis by using plant. So these are the some specification of green synthesis method. These are the applications of green synthesis method. Use renewable feedstock, increase energy efficiency, and many more. So result in discussion, I have done 3 characterization in my research work. First is X-ray diffraction. So X-ray diffraction is a powerful technique which determines the crystallographic structure and particle size of the material. So this is the graph of my XRD, intensity versus 2 theta. So the average crystal size is calculated by Debye-Cheval formula is found to be 10.21 nanometer, and the spacing for the first plane 111 is found to be 2.42 angstrom, and the lattice parameter is calculated by Bragg's formula is 4.17 angstrom. These are the some calculations which I have done for particle size. The average particle size is 10.21 nanometer, and the D spacing for each planes. This is the calculation for lattice constant. The average lattice constant is 4.17. This is a table for various peak, that is 2 theta angles, D spacing and planes, HKL planes. So next technique is FTIR, Fourier transform infrared spectroscopy. In this technique, we find our which functional group present in our material. So, and it is a vibrational spectroscopy. So this is the graph, percent transmissions versus wave number. So the peak represent 3,456 is a phenolic group, and 1,679 represent the carbonyl group, and my nickel oxide represent 570 at the frequency of 570. There are two regions, that is functional group region and fingerprint region in FTIR. This is the table for wave number, bond and functional group present in my material. So the last is UV visible spectroscopy. UV visible spectroscopy determine how much a chemical substance absorbs light, and it is based on Beard's-Lambert's law. So this is my UV graph, absorption versus frequency. So the absorption spectrum is found to be 330 nanometer, which corresponding to band gap of 3.7 electron volt. And tau plots is another way to find the energy band gap. So in this way, I conclude my report using beta vulgaris extract to synthesize nickel oxide nanoparticles. Plant-mediated synthesis of nanoparticles has several advantages over physical and chemical. And I have done characterization, X-ray diffraction, which shows the crystalline size is found to be 10.21 nanometer. UV visible spectroscopy shows the absorption band at 330 nanometer, and confirmed nickel oxide nanoparticle formation, and Fourier transform shows the different functional group present in my region. These are the references I have used on my research work. Thank you. I would like to thank the HOD of my department, Evika Vande sir, my college KSKW, my colleagues, teaching staff, non-teaching staff. Thank you so much for supporting me throughout my research work.
Thank you for your presentation. I request participant to ask the question. If you have any question, please. Okay, thank you. Now we will start with the next participant, next presenter, Ms. Katore Kajal Anil. She is going to present on the Lawsonia interim sleeves extract mediated synthesis and characterization of CDS quantum dots. Please start.
Just 1 minute, sir.
Okay.
Good afternoon, all of you. Today I reported my research work on Lawsonia inner sleeves extract mediated mediated from green synthesis and characterization of CDS quantum dots. Okay, I select green synthesis method because it is eco-friendly, non-toxic compared to the conventional and chemical method. The synthesized series quantum dots are characterized by XRD techniques, and it is gives average size, that is the 4.27 nanometer. And next, FTIR analysis shows the presence of hydroxylic group, nitriles group, alkenes, and carboxylic acid. UV spectroscopy analysis reveals that band gap energy of 3.4 electron volt, which is a higher value compared to the bulk band because of size confinement effects. Serious quantum dot can be explored for the various biomedical applications such as antibacterial, antibiofilm, anti-cancer, etc. So nanotechnology basically deals with 1 to 10 nanometer of particle size. And here you can see that nanotechnology is a revolutionary technology that has application in many fields such as medicine, food, cosmetic, agriculture, some industries, etc. Okay, as the nanomaterial size 1 to 10 nanometer, or if it is less than exciton Bohr's radius, then it is known as a semiconductor quantum dots. My synthesized series quantum dot Bohr radius is 3.4 electron volt. It is less than the exciton Bohr's radius, that is the 5.8 nanometer. So you can see here as the size of quantum dot is changes, its optoelectrical properties also get changes. Sirius Bohr's radius is 5.8 nanometer, then they are said to be the Sirius quantum dots. Here you can see crystal structure of cadmium sulfide, that is the hexagonal and cubic. Many CDS used for the photoresistor, thin film, transistor, transducer, solar cell, electrochemical depositions, etc. Here, there is 3 methods to synthesize the nanoparticles, but I select biological method because it is eco-friendly, non-toxic. That's why there is 2 approaches for the synthesis of nanomaterial. Here, we use bottom-up approach. Greens in here, you can see by the following, just 1 minute. Here is, you can see some advantages of green synthesis. And like the here, you can see following way I synthesis that serious quantum dot. And we can use the following formula to calculate the weights in gram for the required material. In green synthesis method, plant act as a capping agent. So I select Lavosonia inermis leaves, which is belong to the Lythrosia family. And these Lavosonia consist of some phytochemicals also, that is butylene, lavozones, phenol, etc. So by using Lavosonia leaves, we synthesis serious quantum dot, which are characterized by the XRD technique. For that, in this technique, we use copper K alpha as a source. And on next slide, you can see result of the XRD in a graph form. By graph, we calculate the average crystalline size by using the Rebbe-Scherer formula is found to be the 4.27 nanometer. And here we calculate the average dispersing by the Bragg's formula is found to be the 2.01 angstrom for the plane 220 and 3.3 angstrom for the plane 110 and 1.7 for the plane 112. And the lattice parameter for the CDS quantum dot is 5.27 angstrom. And CDS quantum dot characterized by the FTIR techniques also, which shows the presence of here some calculations also. And CDS quantum dot characterized by the FTIR technique also, which shows the presence of nitrile groups, alkenes group, carboxylic acid, cadmium sulfide, etc.
Kajal, please conclude.
Okay. So Plant-mediated synthesis of nanoparticles have several advantages over the physical and chemical method. CDS quantum dot synthesis by the green synthesis method with a loose extract of Lavosonia inermis. Here, the prepared CDS quantum dots average nanoparticle size was found to be the 4.27 nanometer determined by the XRD techniques, and the absorption spectrum maximum for the CDS as 364 nanometer, which is correspond to the band gap 3.4 electron volt. Synthesis CDS quantum dots can be explored for the various biomedical applications such as antibiofilm, antifungal, anti-carcinogenic and anti-cardiac activities, etc. So here are some references that I used. Okay, I would like to say thank you, Principal Sir and HOD Sir of my college. Thank you.
Thank you for the presentation of synthesis and characterization of CDS quantum dots. I request a participant to ask any questions. If you have any question, please. No question, then I would like to start with the next presenter. Taukunde Vanita Padmana. She is going to present development and validation of RP-HPLC method for estimation of mesalamine in bulk and formulation.
Hello.
Yeah.
I'm audible?
Yes, please. You can start.
Yes, sir. 1 minute.
Please finish in the given time.
Okay, sir.
Hello.
Yes, sir.
Please start.
Yes, sir. I'm sharing screen.
Okay.
It is visible, sir?
Screen is not visible.
Sir, can I share my PPT for you?
Yeah.
In a group?
No, just start here.
Hello? Yes, sir. Can I share my PPT for you, sir?
No, just start here.
Because something problem is creating here for sharing screen, sir.
Hello, Mane sir.
Yeah.
If there is a problem for conducting this presentation, please take next participant.
Okay. No problem.
Okay.
So we'll go with the next participant, Aniket Sapkar. Is going to present smoking status in younger generation, a review of available reports. Aniket Sapkar, please start your presentation. Hello.
I think Sapkar is not there.
Hello, Tomre sir.
Yes,
hello.
Sir. Now, how many participants are there?
This one is the last, sir.
This presentation will be last presentation, sir. I think Sapkar is not there, sir.
Okay, sir.
Dr. Mane, sir.
Yeah.
Mr. Sapkar is not there in the group.
So can we
Yeah,
conclude
please
the session?
conclude, sir. Yeah.
Okay,
Okay.
sir. Okay.
So I'm thankful to this organizing committee to give me a chance for this session, to chair this session, and thankful to presentation participants. Nice presentation is there. So I would like to conclude this session, this session, and I will hand over the conference chair towards the convener of this conference.
Okay, sir. I am very thankful, sir. Manu, sir. Are you hear me?
Yes, yes, sir.
Okay, I am very, very thankful to you for this chairing this session. Also, I am very thankful to some participants which that are researchers. They are giving their oral presentation, which is very informative. And lastly, I thanks one again. Okay. Now over to you, Thomre sir, our active convener of this.
Okay, sir. Thank you, Dr. Mane sir, for conducting oral presentation. Thank you. Now I pay the vote of thanks. We are very much thankful to Chairperson Dr. S.M. Mane for valuable discussion and handling session. I am also grateful to Mr. Lokhande, Ms. Gaikwad, Ms. Sheikh, Ms. Katore, Ms. Chaukhunde, Mr. Aniket for their research oral presentations. I am also thankful to the participants, organizer, technicians, colleagues, and non-teaching staff for their efforts. I declare today's sessions are over. Let's meet tomorrow with same e-conference with same theme. Thank you very much. Have a good time. Thank you.
Yeah, good.
One more request to participant. In a WhatsApp group, I have shared one link for certificate details. So please fill it correctly so as we can prepare your certificates properly. So after completion of your filling of the Google form, you will get the message to your email. Check that whether it is okay or not. Otherwise, you will get wrong certificates. So my request to all of you, please fill the correct details in the Google form. Thank you. So let's meet tomorrow with same theme. Thank you.
Sir, thank you.